Okay, good morning, good afternoon, and good evening. I'm Bill Ayler, Chair of the 7th International Academy of Astronautics Planetary Defense Conference. Thank you very much for attending. I want to take this opportunity to recognize the conference co-chairs. That's Brent Barbie, Gerhard Drolshagen, Alex Carl, and Nahum Melamed. Each has played a critical role in developing this conference. You'll see more of them as the conference proceeds. Next, I want to recognize and thank the conference sponsors whose logos are on the break slides and on our website. Please extend thanks to these organizations for recognizing the importance of planetary defense by their support of this conference. I also want to recognize Romana Koffler of the United Nations Office of Outer Space Affairs. Romana has been active with the conference series for several years. She's responsible for bringing the conference to the United Nations and has worked with us to make the conference successful. I also want to thank Peter Kron of the ESA Conference Bureau, who continues to provide outstanding technical support to the conference. Both individuals have worked tirelessly to help us organize and present this virtual conference. We are very grateful to the United Nations for providing the WebEx platform for our use, and I want to thank the volunteers from the local organizing committee who are working in the background to help manage the day-to-day functioning of the conference. And finally, I would like to thank Simonetta de Pippo, the Director of the UN Office of Outer Space Affairs, for her leadership and support, and for the support of her UN USA team as we've adjusted the conference to a virtual format this year, and especially for the invitation that we come back for an in-person conference at the Vienna International Center in 2023. Vienna is a great city, and the UN facilities there are excellent. We hope you'll make plans to join us then. Now a bit about the conference proceedings. The conference is organized to enable people in most countries to participate, and you'll see presentations in the 2 morning and 2 afternoon sessions each day from researchers worldwide who are doing work that relates to asteroid discovery and characterization, how we might move an asteroid, consequences of impact should one strike, and issues that might affect the decision to take action to actually deflect a threatening object. All conference activities are recorded, and you can view presentations that are at inconvenient times via the conference website. Also, a number of authors who were not selected for live presentations submitted recorded briefings and posters that are available online. Please take a look at these also. So we're now beginning activities in what we call the conference's green zone. It's a 3-hour block of time we hope will fit viewers and viewing times schedules worldwide. A key activity in the green zone is the hypothetical asteroid threat exercise. The purpose of this very realistic but fictional, and I'll stress fictional, exercise is to have disaster responders, space agencies, national leaders, and you learn about how an actual threat might evolve and the decisions that must be made to prevent or manage such an event. While this exercise involves a fictional threat, we all know that one of these days we'll discover a real threatening object, and we need to be ready. We hope these types of exercises will help us prepare. Discussion of the threat will continue in the green zone tomorrow with a detailed discussion of possible missions to observe or possibly deflect the object, followed by presentations on legal and policy issues that might affect a decision to act. We'll conclude the exercise on Wednesday. On Thursday, members of the media will discuss messaging to the public about an asteroid threat. We'll discuss lessons learned from past disasters that might inform responses to an asteroid-related event. And the Planetary Society plans a special event for conference participants. And on Friday, we'll hear about what we might learn from Apophis, a large asteroid that will pass very close to Earth in 2029. It won't impact, and a proposal for an international year of planetary defense. We conclude the conference on Friday with a wrap-up session and a discussion of next steps for planetary defense. It is now my pleasure to invite Romana Koffler, Program Officer at the United Nations Office of Outer Space Affairs, as well as Secretariat to the Space Mission Planning Advisory Group, which you'll hear more about shortly, to provide her welcome remarks. Romana, you have the floor.
Thank you very much, Bill. And you have very nicely introduced the whole concept of the conference. We are very glad to be able to welcome you here in a virtual format in Vienna. by the Office for Outer Space Affairs, and I'm very grateful to our organizers, partners, the European Space Agency, for their support. As you have mentioned, the conference has a very intense program and is structured around key sessions, panels, heads of space agency panel, for example, on Wednesday. So a few highlights that are really that everybody is welcome to attend to and listen to. Furthermore, I'd like to acknowledge your role as the initiator of this series of planetary defense conferences. Bill Ehler has been instrumental as he started this idea in 2004, and you have attended all the 9 conferences. There are 7 that are hosted by IAA as the holder of the conference. So this is really a great achievement. We do hope to really host the conference at the Vienna International Center here at one of the 4th UN headquarters, and in 2023. And I know we are very tight on program, so without further ado, I would like to give the word to you back, Bill, to introduce the next speaker or the next presentation, please.
Okay, thank you very much, Romana. Okay, as you know, the conference is sponsored by the International Academy of Astronautics, and we are pleased that Jean-Michel Contant, the Secretary General of the Academy, has provided a short video introduction to the IAA. Please start the video.
There is sound sync, Romana.
1960 by Theodore von Karman. The Academy hosts this conference, and it is interesting to remember what is the Academy. Founded in 1960 by Theodore von Karman, the Academy was having a president very charismatic and having a lot of international reference. There are a lot of space pioneers that were members of the Academy. One of them is Hermann Ober, and also Irene and Eugene Sanger-Bread. In Russia, Tikhon Rahov was working with Sergei Korolev, and Valentin Glushko. Hermann Ober was having a very special student named Werner von Braun. In 61, Yuri Gagarin made the first flight in the world, and rapidly after that became honorary member of the Academy. Valentina Tereshkova is still honorary member of the Academy, and Alexei Leonov, who died last year, was also very active. In America, at the time of the first satellite Explorer 1, the 3 persons on the photo, Pickering, Van Allen, and Werner von Braun, were all members of the Academy. There was also several founding members like Andrew Halley, and in Russia, a long series of famous names. You may identify, for instance, Keldysh, that was member of the Academy and received the Guggenheim Award in 1965. We created a journal, Acta Astronautica, initially with reverse name and for grammatical reason, and this journal was having on the first issue of the journal all the famous name of the pioneer of space activity. They were all listed in the first issue of the journal. It is interesting to see that very shortly after the creation, the Academy was already working on several committees, and one of them is the Lunar International Laboratory, and this is interesting to notice this info. Doug Draper became president, and he was the inventor of the gyroscope, followed by George Muller, who was also president after him and NASA administrator for manned space activity. And here is George Muller in photo together with von Braun at the time of Apollo 11. Apollo 11 was a team of 3 persons, 2 of them working on the moon, and they were all members of the Academy. And today, Buzz Aldrin is still active and was at our last event. In Russia, Valery Polyakov was the one with the longest time in orbit. And in the early 80s, many scientists receiving awards like Broglio, Galeyev, von Karman award, and Arthur Clarke receiving the award as well. In 2003, Yang Liwei became the first astronaut of China, a member of the Academy. The Academy is an honorary organization with 1,200 members from 89 nations. And the membership is by election, and each year there are about 50 new members, and they are in 4 disciplines: basic science, engineering, life science, and social science. There is an award named the von Karman Award, and this award is given to scientists and experts from the beginning of the 80s. The award is recognized by the United Nations, and the journal today have 700,000 downloads each year since 2018. We have 25 to 30 conferences, and we pioneer several concepts over the year. For instance, the small satellite concept was introduced by the Academy in 1984, and it became a very popular concept after that, but this was the first time that the Academy introduced the concept. And it was done on the occasion of a study to oppose the long program of the Space Agency that was over 10 years. And the concept of a small satellite was a short-term program with 1 or 2 year development before flight. The Academy had 3 head of agency summits, and they were collecting most of the space agency leaders over the world. The Academy published dictionaries and have more than 70 studies published, and about 40 in preparation. We also have 4 book series, and among the studies, several of them were related to the subject of space and study dealing with the threat to Earth from asteroids and comets. The first planetary defense was held in Granada, in Spain, hosted by the Academy. The second was in Bucharest, Romania. The third one was in Flagstaff, Arizona. And this place was chosen because there was realistic consideration around the conference place. The fourth one was in Frascati, Italy. Tokyo for the Planetary Defense Conference following. And the last one was Planetary Defense in Washington, where several statements were presented. And for instance, there was a statement on Apophis, and this is some of the highlights of the conference.
Mm-hmm.
We have a planetary defense conference that is absolutely well attended with over 800 participants, and the program is highly dense, and I wish you a good meeting, and thank you.
Thank you, Jean-Michel. Now I'm pleased to introduce our keynote speaker, a person who actually has an asteroid named in her honor. Simonetta de Pippo, Director of the United Nations Office for Outer Space Affairs. Simonetta, you have the floor.
Hello, can you hear me?
Yes, you sound fine.
Okay, Bill, sorry, I had to connect for the audio with my phone because I was not able to hear you, but I believe I managed.
You sound good,
a little bit of IT skills. So thank you very much, and it's really a pleasure for me to welcome you all to this 7th IAA Planetary Defense Conference. Well, every 2 years, this conference brings together world experts to discuss what's known about potentially hazardous asteroids and comets and how we might mount a defensive action in case one is on a collision course with Earth. I would like to thank the International Astronautical Association, IAA, the holder of this conference, as well as our partner, the European Space Agency, for their support. Let me also extend a warm thank you to our host country, Austria, the Austrian Research Promotion Agency, and the Austrian Space Forum for their engagement. Initially planned as an in-person event at the Vienna International Center, unfortunately, this conference is yet another event moved to the online environment. I'm already looking forward to 2023 with hope that we will be able to engage personally. Looking at the bright side, however, switching to the virtual format has allowed us to truly achieve global reach. And it is exciting that we have more than 900 registrations probably and counting to the event. Such figure also underlines the importance of the topic. Throughout history, near-Earth objects have manifested their destructive power. In this regard, I cannot thank enough the Association of Space Explorers. After their proposal to COPIUS, the General Assembly in its resolution from 2016 proclaimed the 30th of June as the annual observation of the International Asteroid Day. By the way, I'm often joke in saying that it's also my birthday. So this day represents a commemoration of the Tunguska event, the Earth's largest asteroid impact in recorded history. International Asteroid Day encourages reflection on the potential impact hazards of asteroids and the global undertaking in this area, and it is also integral to the effort in raising public awareness about these risks. As we aim to build more resilient societies, awareness on NEOs must fall into the purview of challenges we strive to address collectively. Dealing with such a hazard must inevitably be a joint effort in the interest of public safety. And it must be a holistic one as well, encompassing the identification of objects that pose risk of impact and planning a corresponding mitigation campaign. For these reasons, the international space community has recognized the United Nations as one of the main fora for the coordination of mitigation efforts and a platform to advance international cooperation in relevant areas. The Committee on the Peaceful Uses of Outer Space plays a leading role in this regard. Established in 1959, COPIUS serves as a primary UN body for coordinating and facilitating international cooperation in space activities, and its global participation underlines the unique nature of the committee. Following Unispace pre-conference in 1999 and its outcome document, the so-called Vienna Declaration on Space and Human Development, an even stronger collaboration was envisioned to deal with the potential threat posed by NEOs. The establishment of the action team on NEOs and the addition of NEOs as a new agenda item are the legacy of this declaration, opening new chapters of cooperation under the UN. As a culmination of these efforts, the dedicated working group on NEOs was founded under the agenda item of the Scientific and Technical Subcommittee of COPIUS. And in 2013, a great success of a multi-year multilateral effort, the idea of the International Asteroid Warning Network, IOWN, and the Space Mission Planning Advisory Group, SAMPAGE, was born. These two new entities, formally created in 2014, are now the leading bodies for a coordinated international response to the NEO impact threat. As this area is crucial to ensuring human security, the UN continues to facilitate the processes for developing an international response to a NEO impact threat. Here, let me delve quickly into the role of the Office for Outer Space Affairs. Acting as a gateway to space in the UN system, UNUSA is uniquely positioned to foster cooperation in space affairs, also in the perspective of space security and the field of planetary defense. We attach great importance to the work done by SAMPAGE and IOWN and are closely engaged with these bodies. Besides our mandate as Secretariat of SAMPAGE, UNUSA, we at UNUSA have always fostered our observer status to both entities. Additionally, through IOWN and SAMPAGE, UNUSA facilitates the dissemination of information related to NEOs to UN member states. Important linkages are also being made with civil protection communities, including through our UN Spider program and its global network of regional support offices. The main goal of this effort is to sensitize states and their relevant national authorities to the existence of NEOs as potential natural disaster hazards, and to address this as part of their national emergency response and preparedness strategies. With this, we address what the UN member states called for in the annual General Assembly resolution on international cooperation in the peaceful uses of outer space. The goal of ensuring that all countries, in particular developing nations with limited capacity for predicting and mitigating a NEO impact, are aware of potential risks and ensuring effective emergency response and disaster management in the event of a NEO impact. And UNUSA is uniquely positioned in the UN Secretariat. Recently, we became a standalone entity, underscoring the importance of space for the current leadership. As the director, I'm also now serving as the special advisor to the UN Secretary General on Outer Space Affairs. In this regard, I'm doing all in my power to bring space-related topics and issues to the highest level of political consideration and discourse. And I can assure you of my full support towards global cooperation on NEOs. Ladies and gentlemen, as we look through the program, I'm certain that we have plenty of interesting and engaging discussions ahead of us. I know that there are several extremely interesting components of this conference. Highly professionally tailored scientific sessions and presentations will run daily. This includes dedicated panels on legal aspects of planetary defense, disaster management discussions that will also include the team from the UN Spider program, lessons that can be learned from the pandemic, and also much more. We even have an initiative for a UN designated International Year of Planetary Defense. Myself, I look forward to participating in one of the key panels today. In a hypothetical asteroid impact scenario, we will delve into key questions on decision-making and communication with the public and disaster management community. It will also serve as a great opportunity to identify and suggest solutions for potential gaps and hopefully come up with recommendations for the way forward at the policy level. And on Wednesday, I will also join the discussion among the heads of representatives and representatives of space agencies. This will be an apt forum to debate international collaboration and planned missions related to planetary defense. Looking to the future, much remains to be done, but I'm convinced that with outcomes of this conference, we can and will advance planetary defense mechanisms, increase resilience, and build further global awareness at the policy and decision-making level among all relevant stakeholders and the public. I wish you all an engaging and productive conference with a lot of lessons learned in addressing this time a hypothetical asteroid impact scenario. And I hope that next time I will greet you in person at the 8th IAA Planetary Defense Conference in Vienna in 2023. Thank you very much and good luck.
Oh, thank you very much. And thank you for your enthusiasm about this topic. Okay. And for our final speaker, we're honored to have Marius Piso, President of the Romanian Space Agency and the current chair of the United Nations Committee on the Peaceful Uses of Outer Space, to provide welcoming remarks. I want to note that the Romanian Space Agency was the host of the 2011 Planetary Defense Conference, and I want to thank Marius for the hospitality and for a very great conference banquet. It was quite memorable. So, Mr. Piso, you have the floor.
Thank you, Bill, and hello, everybody.
Hi, good to see you.
Good afternoon, good morning, good evening. I will try to give you some words on the international cooperation aspects of the planetary defense issue, and just to mention that planetary defense is by itself an issue of international cooperation. It is defense. It is maybe for the first time that we, the Earth civilization, are preparing to involve in a common defense issue against the potential destructive threats of the universe. And this is an important issue. And this is going above conflicts, above terrestrial things. And this is the reason for the international cooperation and coordination in this area of near-Earth objects, dangerous near-Earth objects, was taken by COPUOS. And this issue has been, as Simonetta mentioned before, since quite a long time on the agenda of the Committee on the Peaceful Uses of Our Space, and it become more and more important. And under the auspices of this committee, there were several recommendations for strengthening international cooperation, and the response to the new impact hazard has been made, leading to the establishment of the I1, as we mentioned, the International Historic Warning Network. So this is the information group, and in the same time, the so-called same page, the Space Mission Planning Advisory Group, which is a working group under the COPUOS. And those bodies provide mechanisms at the global level to address the global challenge posed by NEOS, including detection, tracking, and the impact risk assessment, and subsequently planetary defense measures like civil protection or asteroid deflection even. And this work is definitely facilitated by the UN Office for Our Space Affairs on behalf of the international community. And you see, I1 is linking institutions that are already performing many of those functions, which means discovering, monitoring, and physically characterizing the potential hazardous NEOs. And some of the global issues are accomplished by the International Astronomical Union, and also by the Minor Planet Center, which is located in the Smithsonian Observatory in the US and supported by NASA. And also there are involvements from many countries. Presently, there are 25 official signatories of the I1 Statement of Intent, and probably they will become more. And the I1, as I mentioned, is providing information on potential objects which might endanger our planet. On the other hand, the same page is a group composed of several member states, agencies or intergovernmental agencies that they might be able to plan, to contribute, or to carry out a space-based near-Earth object mitigation campaign, which with responsibilities even in how to provide the potential deflection against such objects. Both organisms, which are complementary, they submit an annual report to COPUOS and to its scientific and technical team, which is happening now, under the quite permanent agenda item of near-Earth objects. And I will not insist too much on the technical and scientific. Okay, sorry for a short technical interruption. I'm sorry, we're interfering a bit with the COPUOS, but it is okay right now. Sorry, it is okay now. Finally, you see, we have today the technical capability to start building some kind of, let's say, perimeter of protection for our planet. And because we have the awareness and we have also the possibility to build this capacity, we bear the highest responsibility for the next generations regarding this issue, and we definitely should concentrate and extend our activity. And I really appreciate the efforts of this community. I still feel that I belong to this community as a scientist. And I'm appreciating also the very international two space missions, which are the Probe 3, which is meant to, let's say, to discover potential dangerous objects coming from the direction of the sun that we cannot observe from the Earth. And this is a fantastic refined mission. This is a coronagraph made of two spacecraft at 140 meters distance, which form a telescope, this coronagraph. And the other one, which is producing by cooperation between Europe and NASA, between the European Space Agency and NASA, the Asteroid Impact Mission, which is called also DART, and which is called also HERA on behalf of ESA, and which is aimed to provide for the first time in our known history, the controlled deflection of a cosmic body. So you see, it is still difficult to change those very, very dangerous and primitive things, but think that also our civilization is still very young, and I repeat, this is one of our major responsibility, and our defense, defending our planet, may also contribute to the increase of collaboration and to peace on the Earth. I thank you very much for your attention.
Okay, good morning or good afternoon or good evening. This is Makoto Yoshikawa from JAXA. This is a second session about Hayabusa 2. We are very happy to have Hayabusa 2 session in this Planetary Defense Conference. Hayabusa 2 has finished its main mission, and now we have lots of data about Ryugu. So today we have 6 presenters. They will talk about the result of Ryugu study and also the future mission of Hayabusa 2. So now, first speaker is Yuichi Tsuda. He's a project manager of Hayabusa 2. Tsuda-san, are you ready?
Yes, I'm ready.
Okay, please start.
Okay. Yes, so this one. So thank you for the opportunity here to talk about the accomplishments of Hayabusa 2 mission in this exciting mission event. I'm Yuichi Tsuda from JAXA, and I'm taking the role of the project manager of this mission. And the Hayabusa 2 is a Japanese asteroid sample return mission, which visited the asteroid Ryugu and returned Earth last December. So in this talk, I would like to cover the top level information of Hayabusa 2, objectives, operation results, and achievements. Then the following talks by my colleagues will cover more in detail about some focused topics. So next slide, please. So Hayabusa 2 is a sample return mission to a C-type asteroid, Ryugu. C-type means a carbon-rich, and Hayabusa 2 aimed at the science to explore the history of the solar system and also the clue to the origin of life. And this chart shows the mission scenario of Hayabusa 2, and it's a 6-year mission launched in 2014 and arrived at the Ryugu in June 2018. And we stayed there for 1.5 years, doing many challenging operations, including landings and kinetic impact. And we left there in November 2019 and successfully returned to Earth last year. So next slide, please. Yes, the appearance of the Hayabusa 2 spacecraft looks like this. So it's a very compact spacecraft having only 600 kilogram wet mass. It is equipped with the ion engine system, which is a fuel-efficient propulsion system. And thanks to that, we could install as many as 15 scientific instruments in this compact spacecraft. Next, please. HYPOTHETICAL arrived at Ryugu on June 27, 2018, and the appearance of Ryugu was very interesting scientifically and hopelessly severe engineering-wise. It was revealed to be a top-shaped asteroid with a diameter of about 900 meters, and it has a retrograde rotation with a period of about 7.6 hours. And the biggest headache for us was that Ryugu was covered with full of borders all over the surface, which forced us to change our strategy for the touchdown operation. So we were obliged to improve our landing performance from the original 50-meter accuracy to 3-meter accuracy. So next chart, please. And because time is limited, let me just show you the summarized accomplishments of HYPOTHETICAL around Ryugu. First, we deployed as many as 4 mobile rovers to the surface of Ryugu. We did a simultaneous operation with 3 rovers, all of which moved and hopped around Ryugu successfully and sent a precious close-up observation data via the main spacecraft. And we succeeded in 2 spacecraft landings for sample collection from 2 different sites. And especially the second one achieved 0.6-meter accuracy landing. Next, please. And we also succeeded in a kinetic impact operation. A 18-meter diameter, 3-meter depth artificial crater was generated by this operation, and the full set of observations of the target terrain before and after the impact, and also the process of the crater forming was obtained. And this will be covered by the next talk more in detail. And then the second landing aimed just 20 meters apart from the crater center to collect the subsurface material exposed by the kinetic impact, which was also successful. And the last thing we did was the 3 small objects orbiting around Ryugu to contribute to the gravity science. Next, please. Okay, so after all these attempts, HYPOTHETICAL left Ryugu in November 2019, and 1 year later, it returned to Earth. The terminal guidance phase consisted of 6 fine trajectory correction maneuvers to guide the spacecraft to a designated landing zone in Woomera Desert, Australia. The reentry capsule was separated from the spacecraft 12 hours before the reentry, and it flew ballistically towards the atmospheric reentry. And 1 hour after the separation, the spacecraft side diverted from the reentry orbit so that it could escape from the Earth's sphere of influence and continue to the extended mission. Next, please. And this is the Earth return fireball of the HYPOTHETICAL sample return capsule. So you can see beautiful light trail in the sky of the southern hemisphere. So after this, at the altitude of about 10 kilometers, the capsule detached the heat shields and deployed the parachute to land softly on ground. Next, please. And the capsule was immediately found by the ground retrieval team. And although there were many additional hardships due to the COVID-19 pandemic, our team could retrieve the capsule and transport it to Japan and brought into the curation facility located in JAXA Sagamihara campus within 57 hours from the atmospheric reentry. Next, please. And then on December 15th, 9 days from the Earth return, we opened the sample container of the reentry capsule and found plenty amount of sample of Ryugu. Our mission requirement was 0.1 gram, but we actually obtained 5.4 gram of sample, which is a total amount from the first and the second landings. And this picture shows sample from the first landing, but we have another chamber which contained the one from the second landings. Next, please. So as I showed, HYPOTHETICAL succeeded in various exploration activities on Ryugu, which includes not only accessing to the Ryugu vicinity, but also roving, sampling, and impacting on the surface of Ryugu. This contributed to science and space exploration engineering, planetary defense, and planetary resource. And especially these successful activities should be a small but significant step toward the future where we can directly affect asteroids for planetary defense purpose. So next, please. Okay, so with that, I would like to conclude my talk. Thank you very much.
Thank you, Tsuga-san. Okay, so let's move on to the next talk. Next talk will be given by Takanao Saiki. He is a project engineer. He will talk about the kinetic impactor. Saiki-san, please.
Can you hear me?
Yes.
Okay. Okay, so let me start my presentation. So I'd like to off my video to because my communication is not good. So okay, so I'm Takanao Saiki. I'm a member of a Hayabusa 2 operation team, and I was responsible for the development of the impact system of Hayabusa 2. Today, I'd like to talk about our impact system and the result of the impact experiment conducted on April 5th, 2019. Okay, next slide, please. Okay, subsurface exploration is one of the most ambitious scientific objectives of the Hayabusa 2 mission. A surface investigation alone is insufficient because asteroid surface is exposed to harsh environments and altered by cosmic rays, solar wind particles, and so on. Investigating the inertial structure and sampling fresh underground materials were required to learn about the evolution of asteroids and our solar system. And investigating asteroid structure is also important for the planetary defense. Thus, the Hayabusa 2 mission includes the artificial crater generation via kinetic impact. Famous small body impact mission like Deep Impact and DART missions use large impactor spacecraft, and huge impact energy can be realized because interplanetary cruising velocity can be used as the impact velocity. So we studied a 300 kilogram class impactor spacecraft in the early concept study phase, but it was not realized due to the financial circumstances. So finally, JAXA developed a new low-cost small impact system called SCI, Small Carrion Impactor. Okay, next please. Okay, the SCI is a small kinetic impact device, sometimes called the space cannon or space bomb. It was mounted on the bottom panel of the spacecraft, and the SCI was used after the spacecraft arrived at Ryugu. Thus, it had to accelerate the impactor by itself because it could not use the interplanetary velocity. The most distinctive point of this device was that it used explosive propellant charge to accelerate the impactor. The powerful explosive accelerates a 2 kilogram copper impactor up to 2 kilometers per second. Its impact energy is much smaller than Deep Impact and DART missions. However, the SCI was very simple. GNC function was not required to hit the asteroid, and its attitude was stabilized by the spin motion provided by the separation mechanism. So we could develop the SCI at low cost. And next, please. Okay, this slide shows the configuration of the SCI. The total mass of the SCI was 18 kilograms, and the mass of the main body is 14 kilograms. Upper left is the separation mechanism. The HERA spring provides the separation force and the spin torque to the main body. And the lower left is the shaped charge to accelerate the impactor. And the upper right is a small safe and arm device newly developed for the SCI. And the middle right is the electric device. It includes a sequencer and ignition circuit. And the lower right is the primary battery, which provides the electric power after release. Okay, next slide, please. Okay, the mass of the shaped charge is 9.5 kilograms. It includes a 4.7 kilogram HMX-based PBX. The acceleration time is less than 1 millisecond. Thus, the spacecraft, the HCI does not require a long distance for acceleration. However, it has a serious problem. The powerful explosive destroyed the HCI main body and scattered many high-speed fragments. And the spacecraft has to avoid the fragments, so complicated operation was required. Okay, next slide, please. Okay, this slide shows the impact operation sequence. Okay, the key point is that the spacecraft must escape to the safe zone behind the Ryugu's rim to avoid the debris from the HCI and eject from the impact point. The HCI is released at an altitude of 500 meters. Then the spacecraft starts the horizontal orbital maneuver and release a small camera called the DCAM-3, which observes the impact phenomenon. Then the spacecraft performed the vertical maneuver to the safe zone. And the impact occurs 14 minutes after the HCI release. Okay, next slide, please. Okay, before the impact experiment, we determined the impact target. The latitude of the impact target was 6 degrees north, and the longitude was 303 degrees. And the target was on the ridge of Ryugu and located near the flat area called S01. Okay, next slide, please. Okay, this slide summarizes the event of the impact experiment conducted on April 5th, 2019. The spacecraft starts descent from 20 kilometers altitude, and the HCI was turned on during descent. And we sent a final go command at 1:05, and the HCI was released as scheduled. And the spacecraft released the DCAM-3 in the escaping phase, and the impact occurred at 2:36. The DCAM-3 successfully observed the impact and sent many images to the spacecraft after the impact. The right image is the released HCI observed by the spacecraft's camera. Okay, next slide, please. Okay, so the DCAM-3 successfully observed the impact. The impact was right-hand figure was captured 3 seconds after the impact. And we can see the ejector from the impact point very clearly. Okay, next slide, please. Okay, and the artificial crater was observed in detail 3 weeks after the impact. We could easily detect the artificial crater. And its diameter was about 15 meters, and the impact position was only 20 meters off from the impact target. And this means that the HCI was released with small velocity and pointing errors. Then we completed the second sample collection, targeting the north of the crater on July 11th, 2019. Okay, next slide, please. Okay, this is summary. The investigation of the subsurface structure and the materials was the new objective of Hayabusa 2 that was not seen with Hayabusa. And Hayabusa 2 was equipped with a compact kinetic impactor, HCI, and a small deployable camera, DCAM-3. And the spacecraft, HCI, and the DCAM worked perfectly in the impact experiment on April 5th, 2019. And a 15 meters class artificial crater was created, and its formation process was observed by the DCAM-3 camera. The impact energy of the HCI was too small to deflect the asteroid. However, the SCI is an important tool for planetary defense because the artificial crater gives us valuable information about the structure of small bodies. Okay, that's all. Thank you.
Thank you for your nice talk, Saiki-san. Okay, so let's move on to the third speaker. Third speaker is Professor Masahiko Arakawa. He is a PI, science PI of SCI. Okay, Arakawa-san, are you ready?
Yes.
Yes.
Hi, hello. I'm Masahiko Arakawa from Kobe University, Japan. I'm science PI of SCI DCAM3 team. Today, I'd like to talk about the main result of artificial impact crater on Ryugu formed in gravity-dominated regime. Next slide, please. So, in the previous talk, Dr. Saiki already explained small carrier impactor in the engineering aspect. So, I'd like to talk in the scientific aspect. The SCI impact experiment on Ryugu was carried out to form an artificial impact crater, and it excavated the subsurface, and we observed the asteroid interior. The deep level camera 3 was planned to observe the eject curtain in order to study the mechanical properties of the surface. So, in the scientific aspect, the SCI impact supported Hayabusa's scientific observation by remote sensing instruments and the sampling at touchdown. Next slide, please. I briefly introduce the instrument for Hayabusa's impact experiment. The SCI was already introduced by Dr. Saiki, so I omit the explanation for it. The DCAM3 means a deep level camera in third generation. The DCAM3 was a tiny satellite composed of optic, sensor, transmitter, and battery. It has spatial resolution better than 1 meter per pixel, and it could take a picture every 1 second. And it had a large field of view, 74 degrees. So this specification enabled us to make in situ observation of the SCI impact on the surface of Ryugu. Next slide, please. I will show you overview of SCI DCAM3 operation. The SCI operation was already explained by Dr. Saiki, so I just talk about the DCAM3 operation. The DCAM3 was separated from Hayabusa 2 during the exit process. The DCAM3 was apart from Ryugu about 1 kilometer and observed the SCI impact just from the side. Next slide, please. I'd like to show the successive images of eject curtain observed by the DCAM3. You can see 6 images taken at from 5 seconds to 500 seconds after the SCI impact. In the first image, labeled A, you can see ejecta generated in the collision, and initially it splayed northward. You see a full plate formation process from excavation to deposition, and it continues for more than 500 seconds. During the crater formation process, we never observed separation between the ejecta curtain and the ground surface. More, we noticed that for first 200 seconds, the crater appears to be glowing. After this close, the ejecta deposition is occurring. These evidences tell us that the SCI crater could be formed in the gravity-dominated region. Next slide, please. This is an enlarged image taken at 200 seconds after the impact by DCAM3. You can see 4 or 5 separated eject rays, and they could be originated by subsurface large boulders. Next slide, please. I'd like to talk about the SCI crater, which is named Omusubi Coloring Crater in Japanese. The left and the middle image show the images taken before and after the SCI impact. So you can easily recognize the SCI crater in the middle image. The crater is a semicircle, so we speculated that the southern crater growth was inhibited by the Okamoto boulder, large boulder. We also found a pit about the size of 3 meters at the eastern end of the large Ijima boulder. Next slide, please. This is a digital elevation map of the SCI crater. According to this map, we measure the crater diameter shown by red broken line about 50 meters. The lip diameter shown by the black broken line was about 18 meters. The pitch shown by green dotted line has a size of 3 meters, and this small hole could be formed on the slightly cohesive layer with a strength of several hundred Pascal. Then we speculated that the Ryugu's surface was composed of at least 2 layers. That is, the cohesive layer is covered with non-cohesive layer with a thickness of about 2 meters. Next slide, please. Finally, I'd like to compare the SCI crater with a crater formed by the ground experiment. We previously formed an artificial crater by the ground test of SCI flight model. The crater was formed on the sand, and the crater size was about 2 meters. The SCI crater was about 7 times larger than that formed on the Earth. So we think that the small gravity 10 to the minus 5 g of Ryugu caused this large difference. So this result can be explained by the conventional crater scaling law for dry sand. Thus, we speculate that Ryugu is covered with sand-like regress without cohesion. Next slide, please. So this is summary of my talk. That's it. Thank you for your attention.
Thank you very much, Arakawa-san. Okay, so next talk will be given by Professor Seiji Sugita. He is a PI of optical navigation camera, and he will talk about the physical property of Ryugu. Okay, Sugita-san, please.
I am Seiji Sugita of University of Tokyo. Today, I'd like to talk to you about physical properties of Ryugu revealed by proximity observation with a HYPOTHETICAL 2 science instrument.
Okay, next slide, please. Next slide. Thank you.
Thanks to the wonderful engineering team of HYPOTHETICAL 2, we had a chance to observe all the way from hundreds of kilometers away from Ryugu, all the way down to 1 meter of a distance at the time of a touchdown operation. And we also had a bonus, big bonus of SCI crater experiments. Then we learned so much about the Ryugu.
Okay, next slide, please.
Based on the observations, we think we learned so much about the asteroid Ryugu. General characteristics are summarized in this slide. First one is that Ryugu is a top-shaped asteroid. It's got probably rubble pile structure, and its spectra is consistent with the thermally metamorphosed CMCI chondrites. And then also the near-infrared spectra shows weak but the significant strength of a OH band that would indicate that there is a presence of a hydrated mineral on Ryugu material.
Okay, next slide, please.
Each of these observations are really exciting, but to my view, one of the biggest surprises is the gap between the actual boulder size and size estimated based on the pre-arrival thermal inertia observation. The former is about 3 meters, the latter is about centimeters. The thermal inertia observed by the ground-based space-based observation indicates about 100 to 300 MKS. So the big difference between the two.
Okay, next slide, please.
Does it mean that pre-arrival thermal inertia observation is somewhat incorrect? That's not true. The best observation result from a HYPOTHETICAL observation yields that thermal inertia is about 300 MKS here. This is absolutely within the range of a error of a pre-arrival observation. Also, there's another surprise. There is no significant difference in thermal inertia between regolith bed and then the boulders. Furthermore, there are some cold boulders. Here is a temperature map. Yeah, those have a very low porosity and then a high density, but those are extremely rare. So vast majority of Ryugu material possessed a very small thermal inertia like 300. This would correspond to tensile strengths much less than 1 megapascal. So Ryugu's material is highly porous, mechanically weak, but its size is very large.
Okay, next slide, please.
Then another question may rise, which is that isn't a fluffy dust layer covering the surface of the boulders, and that would reduce the effective thermal inertia of boulders with a 5 to 7 hours of rotation period. However, the lander mascot had a macroscopic imaging observation and then revealed that those boulder surface is not really covered with a fluffy dust layer. You can see some real clear color variation of bare surfaces of boulders. Furthermore, MARA measurement of a thermal infrared of a fixed point of a boulder on the nighttime of a Ryugu is really consistent with the bare surface without dust layer. If you assume some dust layer, this temperature profile greatly deviate from observation. So those two pieces of observation indicates that there is no thick dust layer on the Ryugu.
Okay, next slide, please.
So how do those Ryugu boulder possess such a low thermal inertia or high porosity? One idea is that those boulders may be bridgers. If it's a monomixed bridger, it's difficult to discern with the imaging data, but if it's a polymixed bridger, including different composition of a class like this, you can clearly see that those are bridger-like structure. And then many of those high albedo material or spectrally distinct materials found to be adhered together or cemented together with the dark materials. Those really strongly suggest that breccia are really widespread on Ryugu.
Okay, last slide.
Here's a summary on conclusions. The take-home message for here is that a bridge structure may be an important cause for Ryugu's low thermal inertia, and a bridge structure may be an important factor to consider for planetary defense of low albedo asteroid. Thank you for your attention.
Okay, thank you, Sugita-san.
Okay, thank you.
Okay, so the next talk is given by Dr. Tatsuaki Okada. He is working for the thermal infrared imager. Okay, Okada-san, please.
Yes, do you hear me?
Yes.
So, thank you. Let me talk about the results of the thermal imaging by thermal infrared imager. TIR, the thermal infrared imager, is a barometer-based thermographic imager, and the updated version will be on board on HERA mission. It images the surface temperature, and from the general temperature profile of one rotation images, the thermal inertia map can be derived, and it can observe the shape of the asteroid even in the night time. So that's a very powerful instrument. So next, please. So the left-hand side is the one rotation thermal image of Ryugu, and the temperature borders are almost the same temperature compared with the surroundings, as Sugita-san showed, mentioned. It is very different from the prediction. That's because the right-hand side, the reference as the model, the borders were considered as dense material and observed as cold spots. but most of borders are high, are the same temperature. So that means the borders, most of borders are highly porous. And the other interesting points are the flat general temperature profile compared to the simple summary model, which corresponds to the highly rough surface on the Ryugu. Next, please. So the observed temperature profile was compared with the simulation of rough and porous surfaces with different roughness parameters and the summary inertia. And the best fit values are adapted for each polygon and plotted on that. Next, please. So this is one of the results of the summary inertia and roughness parameter at the same time. The left-hand side is the summary inertia map, and the right-hand side is the roughness parameter map. The results are shown. Yeah, the summary inertia is typically about a very small value, about 200 to 300, the MTS. This is much smaller than that of the typical carbonaceous chondrite summary inertia. That is about this, beyond the 600. So that's a very, very low value. And the roughness is also very low. But 0.4 is very rough surface, which is consistent with the observation imaged by the ONCT and the surface renders, Mascot and Minerva. So next, please. Another very interesting point is there are some anomalous borders found. One of the core spots, it is correspond to dense borders. And the summary inertia is about 600 to about 1,000. This is correspond to the typical value of the carbonaceous chondrites. Another interest point is a hotspot in the crater. This is anomalously porous hot borders, so the corresponding to the very, very high porosity. The low summary inertia value of the Ryugu is typical when plotted on the diagram of asteroid diameter and the summary inertia plots. And the dense border is a typical value for the carbonaceous chondrites, and the hot porous border is the end member of the very and typical plot on this plot. So next, please. So here's the summary. The surface temperature and the derived summary inertia of Ryugu was imaged by TIR, even in the night or shaded side. The surface of Ryugu is covered with highly porous boulders and rocks, and it should be the low strength. The surface of Ryugu is very rough, with a scale of less than 10 centimeters. So this is the summer index. The variation of porosity is found on Ryugu, indicating the different degree of alteration in the parent body. So thank you very much.
Okay, thank you, Kata-san. Okay, so the final talk in this session is given by Dr. Masatoshi Hirabayashi. He will talk about the extended mission. Hirabayashi-san, are you ready?
Can you hear me?
Yes,
Hello?
I can hear you.
Okay, thank you. All right, so today I discuss the Hayabusa 2 extended mission briefly. Next slide, please. So Hayabusa 2 extended mission, the assessment group has been assessing the extended mission since 2019. The Hayabusa 2 extended mission is a small body rendezvous mission that will use the already flying Hayabusa 2 spacecraft. The extended mission follows its nominal mission. The spacecraft is currently flying without any critical issues. The extended mission will explore both scientific and engineering technologies, especially targeting planetary defense. The target of Hayabusa 2 extended mission will be a very small asteroid, which will be part of one of the most common asteroid population in the inner solar system. Therefore, such an asteroid frequently influences the Earth environment. The extended mission is planned to continue until early 2030s. The mission is about to start. Next slide, please. The rendezvous target is asteroid 1998 KY26, or I call it later KY26. Earlier observations gave us the geophysical properties of this asteroid. The shape is around spherical. The equivalent diameter is around 30 meters. The spin period is around 10.7 minutes. The tumbling mode has not been observed yet. The taxonomy may represent dark materials or possibly carbonaceous materials. Next slide, please. Because of the fast spin, KY26 is likely to have a unique surface and internal conditions. We conducted internal structural analysis by using FEM, which is given on the right plot. Those are showing a normal stress distribution. As you can see, everywhere inside of the body experiences tension. However, if you look at the magnitude of stress, it is around 5 pascals, which is very low. Therefore, we can consider two potential explanations of this asteroid structure. The first explanation may be that this asteroid is likely monolithic, given the formation scenarios. The other explanation is that given the stress level, which is 5 pascals, this asteroid may be rubble pile. Those materials cannot exist in the surface regions unless there is attractive forces, such as cohesion. So if we can observe dust particles or debris regolith on the surface, that indicates the existence of attractive forces. Fractures, craters, and other geomorphological features may correlate with this asteroid's evolution. Therefore, it is very important to conduct proximity operations. Next slide, please. This mission contains 5 phases. Phase 1, which was already done successfully, Earth swing-by operation in 2020. After 6 years, the spacecraft go to 2001 CC21, which is our flyby target. During that operation, we plan to conduct remote sensing observations. The spacecraft coming back to the Earth in 2027 to perform another Earth swing-by operation. The spacecraft goes away, but coming back to the Earth in 2027 to conduct the final Earth swing-by operation. After that, the spacecraft goes to KY26 directly to rendezvous with it. We plan proximity operations including remote sensing observations and mechanical experiments. However, we are currently carefully assessing the feasibility of observations because although the current spacecraft condition is healthy, the spacecraft is getting older. Therefore, it is necessary to figure out what reasonable observation would be. During the extended mission, we will have a long-term cruise phase. Therefore, we will conduct zodiacal light and exoplanet observations by taking advantage of these long-term cruise phases so that we can continue scientific outcomes. Next slide, please. By this, I like to emphasize that we are so thrilled to see KY26 in early 2030s. Thanks, and I'll take questions.
Okay, thank you, Hidebashi-san. So now we start the question and answer session. So if you have questions, please write it in Q&A. So now I see one question in chat and 2 questions in Q&A. So let's start from chat. So the question is from Dan Mazanek. Were all of the samples returned to Earth by Hayabusa 2 expected to be from the low cohesion region of the Ryugu surface? Maybe this question is answered by Arakawa-san.
So we speculate that the top surface of Ryugu is very low cohesive region or non-cohesive region. It may be less than 1 Pascal, something like that. So we speculate that we recover samples such a low cohesion region. That's it.
Okay, thank you. Okay, then in question in Q&A, the question is to Sugita-san. The first one is, what are the components of the breccia structure? Is the high porosity due to large voids in the matrix structure like pumice, or interstitial space among the components, a particle like a pile of sand? Can you answer this question?
Yes, thank you. This is a great question. I actually tried to answer the question, but my answer went to some wrong place. But anyway, my short answer is that your latter option is probably correct. Well, that's our interpretation. Individual class within the boulder seem to have a substantial density or strength. And then the interstitial void may be the macroscopic, the substitute, the substance of the porosity. So it's more like a sandstone or a weak pile of sand. And then there's also some follow-up question or a comment from Tom Statler-san.
Yes.
Yes. Yeah.
Can you?
Yeah. I could write back to him, and then his question or comment is that there's a very recent preprint by Herbert et al. Arguing on the basis of packing theory that the macroscopic porosity, macros porosity of Ryugu is very low, 0.14, and therefore the density of the constituent rock is also low. Can you comment? And then my answer is that we basically agree with this paper's inference that the macroscopic Ryugu could be very low, based on the same kind of a packing theory. Recent paper by Matthew Groth on JGR reached pretty much the same conclusion, slightly different theories. But that's why we believe that the slightly substantial amount of intra-boulder porosity seems to be consistent with the entire picture, like small macroporosity, large microporosity, or interstitial porosity. That's our interpretation. Hopefully we will be able to answer this question by examining the Earth return samples of Ryugu. Thank you.
Okay, so now we have a question in Q&A. This is to Hirabayashi-san. What cohesive strength would be needed to hold together the small asteroid if it is a double pile? Can you ask this, Hirabayashi-san?
This is a great question. Thank you so much. Regarding rubble pile asteroids, there are several papers earlier analyzed it. So usual cohesive strength we consider is around like 100 pascals, a few hundred pascals, based on observation analysis of active asteroids. So this is our understanding. We are currently considering this number would be reasonable. However, we definitely need to analyze that more.
Okay, thank you.
So basically, we're going to be beginning now at exercise session number 1, which is the first notice of a threat. The purpose of these exercises is to present a fictitious threat, just as a real threat might be presented, and to follow the decision-making process as the threat evolves. Fortunately, we have experts playing key roles today who would likely play similar roles should an actual threat be discovered. The first is Kelly Fast, coordinator of the International Asteroid Warning Network, or IWAN, who will describe IWAN's responsibilities. Kelly will introduce Paul Chodas, director of NASA's Center for Near-Earth Object Studies, or CNEOS, at JPL. Paul will provide information on the threat. Paul will introduce Lorian Wheeler, risk assessment lead for the Asteroid Threat Assessment Project at NASA's Ames Research Center, who will discuss possible consequences should the actual asteroid actually strike Earth. And Lorian will introduce Gerhard Drolshagen, co-chair of the conference and also chair of the Space Mission Planning Advisory Group, or SAME-PAGE. Gerhard will highlight that group's responsibilities. After these presentations and after a break, Romana Koffler will introduce a panel of individuals who've been listening to these presentations, who most likely know very little about the subject, but may be in a position to make some decisions should a real event come along. And they'll be discussing and needing to make some decisions as to next steps for this exercise. So now let's get the exercise started. Kelly Fast, over to you.
All right, thank you, Bill, and greetings, everyone. I appreciate this opportunity to brief the International Asteroid Warning Network to you so that you can have more background as we go into this scenario. The International Asteroid Warning Network, or IWAN, was established in 2014 as a United Nations recommended international collaboration of astronomical organizations involved in discovering, tracking, and characterizing NEOs that pose an impact hazard to Earth. And so IWAN is not an independent organization of its own, it is a collaboration. Signatories to the IWAN Statement of Intent are all involved in planetary defense operations at some level. They bring to bear a variety of ground-based and space-based telescopic assets to discover and observe NEOs, as well as abilities in orbit computation, potential impact prediction, and modeling of potential impact effects. IWAN has a steering committee representing the core capabilities of IWAN, which meets twice a year. And its discussion topics also include work items in coordination with its counterpart, the Space Mission Planning Advisory Group, on which Gerhard Drolshagen will brief you later. NASA organizes the meetings of the IWAN steering committee, activities like observing campaigns, and supports the iwan.net website, which is hosted by the University of Maryland. Do you have my slides available there, or will I need to show them?
Yes, we'll display them, Kelly.
Thank you very much, Romana. And this presents sort of the organization of IWAN relative to the UN COPIS and the Office of Outer Space Affairs. Again, it's a recommended collaboration. And in the event of the discovery of a potential impact or hazardous to Earth, starting when the impact probability reaches or surpasses 1%. IWAN, through its steering committee, would report information to the UN Office of Outer Space Affairs, which would disseminate the information to its member states through the processes that it employs. Now, IWAN is a collaboration. Signatories to IWAN are all independent entities, and they would also follow whatever their own notification processes might be, if any, in their own countries. And in fact, it is important to remember that NEO data, such as the Minor Planet Center data, are all publicly available. And it's all but certain that there will already be news and social media reports in the event of the discovery of a potential impactor. But IWAN's goal, through its collaboration of signatories involved in planetary defense operations, is to provide the most credible, accurate information available for decision makers and the public. And if I could have the next slide, please. And there are now 30 official signatories to the IWAN Statement of Intent, representing independent astronomers, observatories, and space institutions from 15 countries and international European organizations. And I'm running out of room on the slide. We're getting so many signatories, which is fantastic. And as many of you know, since you participated, IWAN is wrapping up a coordinated observing campaign of the potentially hazardous asteroid 99942 Apophis. And IWAN also participated in its own exercise that treated Apophis as a newly discovered asteroid in order to test the worldwide observing and modeling capability. But in the exercise this week involving a hypothetical asteroid and its impact scenario, Paul Chodas will issue updates on the hypothetical scenario on behalf of IWAN. And now what does that mean? As the director of JPL's Center for Near-Earth Object Studies, Paul is part of NASA's contribution to IWAN as a signatory, and Paul is a member of the IWAN Steering Committee. So in that capacity and for the purpose of the exercise this week, Paul will speak on behalf of IWAN, the collaboration of IWAN signatories, as he gives the updates on the hypothetical scenario. And so in closing, further information on the International Asteroid Warning Network is available at iwan.net. IAWN.net. And again, thank you for the opportunity to brief PDC on IWAN. And so now I will pass it over to Paul Chodas of JPL Center for Near-Earth Object Studies to present the hypothetical scenario.
Thank you, Kelly. Let me get my screen shared here. Can you see my slides?
Yep, looks good. Put it full screen though.
And I probably have to switch the screens. Hang on one second. Okay. And we'll get rid of this. Okay. So as Kelly mentioned, I'm Paul Chodas, director of the Center for NEO Studies at Jet Propulsion Laboratory in California. It's my pleasure to be your guide through the 2021 PDC hypothetical asteroid impact exercise. Before we get going on that, I need to say a few things about the exercise. I went a little too far. The exercise will be presented in a series of 4 injects over 3 days of the conference. And the scenario date will be advancing from one inject to the next. So the presentations will only be reflecting the knowledge we have as of each scenario date. So the first presentation will be for today, actually, as we've had a website already up. You can see the URL there, PDC21 on the CNEO's website. The inject page is for the day 1 inject, that is what I'm presenting right now, is up as well as of just a few minutes ago. Now, day 0 has been up for months. So we've had the setup of the exercise well established for months, and there have been numerous papers at this conference that have discussed that exercise. Day 1 will be a revisit of the day 0 material. We'll go into greater depth and we'll provide results of the impact analyses as well. And before I get any further, I want to point out that we're going to have, that this is a hypothetical exercise. The asteroid is fictional, and we've marked our presentation materials with exercise only and all of that sort of thing. So please pay attention to the fact that this is a hypothetical exercise. Okay, let's start. And here we go. So, beg your pardon. This is my title slide. The day of the exercise is today, April 26th. And the headline is Newly Discovered Asteroid Poses a Risk of Earth Impact in 6 months. The information about the day one inject is all on this slide. So this is our summary slide. An asteroid is discovered on April the 19th, only a week ago, by Pan-STARRS survey in Hawaii. The observation and discovery is confirmed the following night, and the Minor Planet Center designates the asteroid 2021 PDC. There's a clue there that it's not a real asteroid because there's 3 letters in the designation. The asteroid is tracked nightly, and they provide observations that are essential for computing its orbit. The asteroid at discovery is very distant. It's 35 million miles away and at about magnitude 21.4. And it will remain far away until September, when it will start to approach very close to the Earth. Now, as happens with all asteroids, impact monitoring systems at NASA, at CNEOS, and at ESA and the NEOCC, both assess that the asteroid has a chance, but will monitor the impact possibilities of the asteroid. And in this case, they'll detect the fact that this asteroid could impact the Earth on October the 20th, 2021, only 6 months from now. And they'll detect that really on the day or two after the discovery. Now today, after a week of tracking, the impact probability, which has been steadily rising over the days, has reached 5%. And in my future slides, I'm going to talk a little bit about how we compute impact probability. So I'll provide some background and tutorial material on that. The size of the asteroid, however, is highly uncertain. Based on its brightness, we think that and nominal ideas of assumptions of its reflectivities, the nominal size range is estimated to be between 800 to 200 meters, 80 to 200 meters in size. But that's just the nominal size range, and I'll explain this in a later slide. If you consider all of the uncertainties, the full potential size of this asteroid is somewhere between 35 meters and 700 meters. And I'll explain a little bit why that's so uncertain. Now, with the 5% impact probability and the size of the asteroid, this asteroid meets the threshold criteria for action by both the IWAN and the same page. Now, the orbit of the asteroid is mostly outside the Earth's orbit, as you can see in this diagram. The 2 orbits intersect at the red box, as you can see in the upper right. But the discovery of the asteroid is in the lower left. And I've shown the Earth position and the asteroid position on the date of the discovery, April 20th. They're about 35 million miles apart. Now, the asteroid takes 1.4 years to complete one of its orbits around the sun. And of course, the Earth takes 1 year. So as the asteroid goes around the sun and the Earth, in fact, the asteroid will only take half an orbit before the potential impact on October the 20th. Now, not shown here is the fact that the asteroid orbit is tilted about 16 degrees to the Earth's orbit. So let's look at this idea of uncertainty region and impact probability. I'm going to talk a little bit about how we compute impact probability. So to assess the chance of impact, we need to predict the position of the asteroid when the Earth crosses its path. Predictions of future positions are always uncertain at some level, and so we form an uncertainty region around the predicted position, and then we sometimes visualize that region by filling it with tracer points, and you can think of them as virtual asteroids. Now, since this asteroid has only been tracked for a week, the uncertainty region on October 20th will be very large. In fact, it's much larger than the Earth. If the Earth then passes through the uncertainty region, then an impact is possible. And in fact, you could get an idea of the the impact probability by just counting the tracer points and seeing how many or what fraction of the points impact the Earth. And further to that, you could, if you actually calculate where those points hit the Earth, you can compute where the asteroid might hit on the Earth, the impact region. So here now is a little depiction in red dots of the uncertainty region of this asteroid at the time that the Earth passes through its orbit. Now you can see the moon's orbit is shown as the circle there. So the uncertainty region is a fair fraction of the moon's orbit in size. It's very large. 5% of those dots will intersect the Earth, and that's where we get the impact probability for this asteroid. Now, as more observations are made of the asteroid, and I'll talk about observations in a minute, the uncertainty will shrink and we'll get better and better predictions. This following sequence of slides shows you roughly how the uncertainty region intersects the Earth. So this is a sequence, and I've shown 2-hour time ticks on the blue line, which kind of traces one of the points. The circle on the left is the moon's orbit, the arrow points to the sun, and the green circle is the Earth. So if we just take 2-hour time steps, so this is about 12 hours before, if we just take 2-hour time steps, we can see how the uncertainty region approaches the Earth and can intersect the Earth. And as I say, about 5% of those points impact the Earth. So that's how the uncertainty region applies to the impact probability. Now, where could this asteroid impact? Based on the current knowledge, and because the uncertainty region is so large, essentially a whole hemisphere of the Earth is at risk as the Earth goes through this uncertainty region. In fact, a little bit more, as you can see in this diagram, I've shaded in purple the regions of Earth that are at risk of this impact. And in fact, it covers about 2/3 of the Earth's surface. The reason it's more than one hemisphere is because the Earth's gravity tends to focus the trajectories that might miss the Earth. It tends to focus them and cause them to bend inwards towards impact. So that's the uncertainty region that we'll be dealing with on day one. And as you can see, it's extremely large. Now, observations. Future observations are critical for the scenario because they give an indication of how the uncertainty region will shrink and how the impact probability might change. The IWAN would be helping to coordinate the international observation efforts for this asteroid as they do for many other asteroids. Now, since the asteroid has only been tracked for a week, continued tracking is essential to get that uncertainty region to be smaller and to get the most accurate possible orbit and impact assessments. Now, a little bit of information here. Orbit accuracy depends critically on the length of time over which an asteroid has tracked, and we call that the data arc. So the longer this length of time, the longer the data arc, the more accurate the orbit will be. A little detail here, for this particular asteroid, in this scenario, a few observations were found before the discovery date, and we call these pre-discovery observations. So they were found in images taken just on the days before this asteroid was discovered. And that actually extends the data arc a little bit and helps with our, to reduce the size of the uncertainty and helps to us to evaluate the possibility of impact. Now, impact probability could change dramatically over the next week because this data arc, which is only 7 days now or so, will be changing in size by a fair fraction. If the asteroid is on an impact trajectory, observations over the next week will likely push that impact probability up to as much as 30%. That's how much we expect the uncertainty to shrink. If the asteroid is not on an impact trajectory, the probability might still rise for a while, but eventually it will drop to 0 as we get a better and better orbit. Now, this particular asteroid turns out is observable until October, so we will be able to continue to shrink the uncertainty region on the asteroid. But I point out that the asteroid will be faint and the observations will be difficult as the object actually is going near the Earth and is getting towards the twilight sky. One final technical slide. Will the impact probability go up or down? Well, that depends on what the uncertainty region does. And in the upper right here, we've shown a sequence of possible uncertainties for the asteroid and at the time that the Earth passes by. Now, if the uncertainty region shrinks as you get more and more data, and the Earth remains inside that ellipse, then the impact probability will rise. But if the region shrinks and it shrinks so much that the Earth goes out of that ellipse, then the impact probability will go down. And we can't really predict ahead of time whether the Earth will remain inside the uncertainty or not. Most likely, the region will shrink entirely away from the Earth and the impact probability will drop to 0. But it could, if the Earth remains in that shrinking uncertainty, the impact probability could go to 100%. My last topic I'd like to talk about is this business of the size of the asteroid. Now, typically we measure the brightness of asteroids optically, and we use all of those measurements to compute an intrinsic brightness. We call it an absolute magnitude. And that is a kind of the magnitude of the asteroid at a standard distance from the Earth and Sun. And that can be a proxy for the size. We could use a little algorithm to convert the absolute magnitude to a size if we knew the albedo, the surface brightness of the asteroid, but that is not known, and it can vary widely from one asteroid to another. And so I've given some examples in this little table here. If the asteroid has an extremely bright surface, it could be 60 meters in size. If it's just a bright surface, 80 meters, average 140 meters. If it's dark surface, it could be 200 meters in size. And if it's extremely dark, it could be, many hundreds of meters. Now, the asteroid brightness on the sky would be the same in all of these cases. So we can't tell the difference. They all look the same in our images. Typically, for nominal computations of asteroid size, we take the middle 3 lines of this table. So we would say the asteroid, is 80 meters to 200 meters. But to be rigorous, we have to consider the cases that it's extremely bright or extremely dark. And furthermore, if we incorporate the uncertainty in the absolute magnitude, because all magnitude measurements have uncertainty, the full size range would be 35 to 700 meters. Now, how can we get a more accurate size on an asteroid? Well, you can observe it with space-based IR. Infrared will give you as a direct measurement of the size of an asteroid. And in fact, NEOWISE is the little satellite that could. It's on its extended mission. And in fact, this asteroid will theoretically pass through the field of regard of NEOWISE. And we'll hear a little bit about that in other papers in this conference. The second method would be to observe it with radar. And that often gives you not only the size of the asteroid, but its shape. Unfortunately, this asteroid remains too far away, so it's out of range. So radar is out of the question. We could send a reconnaissance mission, and that we will discuss the possibilities of missions later. Brent Barbie will have a talk tomorrow on that. So what is the implication of the size? Well, if we put in red here, if I circle the size of various asteroids and look at the possible effects, the type of event in the second column there, if it's a 50-ish meter, it's local scale devastation. If it's 140 meters, it's regional scale devastation. Now, I'm showing the nominal size range here, but if we actually go to the full size range, you can see that the amount of devastation could be extremely serious on the high end. And so it's very important to consider the large end of the size range. Now, the next speaker is, I'd like to introduce Lorian Wheeler. She's the risk assessment lead for the Asteroid Threat and Assessment Project at NASA's Ames Research Center. And she'll talk about the impact, possible consequences of this asteroid if it actually strikes the Earth. So over to you, Lorian.
All right, good morning, everyone. I'm just going to share my screen here. If you could pass me the ball, Romana. All right, is that coming up?
Yep, looks good.
Great. All right, so as Paul said, my name is Lorian Wheeler. I work on the Asteroid Threat Assessment Project at NASA Ames Research Center, and I'm going to present the impact risk assessment for today's hypothetical impact scenario. And again, emphasis on hypothetical. So assessing potential impact threats is a challenge because it involves many unknowns, some of which Paul already mentioned. So these include whether the asteroid will impact Earth at all, where it could impact, its size and potential properties, and how much damage it could do, depending on how it could break up, airburst, or impact. In order to assess the risk posed by these kinds of scenarios, we have a probabilistic asteroid impact risk model, or PAIR for short. It uses fast-running physics-based models of asteroid entry and damage to assess millions of impact cases representing the range of unknown factors. The asteroid properties are sampled from distributions that are based on both general asteroid characteristics and along with any observational data for the specific object. The potential impact locations and probabilities are provided by the CNEOS orbital modeling that Paul has just presented. And for each of these cases, the entry and breakup is then modeled to estimate the airburst altitudes or surface impacts, and then the resulting damage is then also modeled for various hazards. These include blast damage, thermal damage, tsunami inundation, and for very large impacts, global effects. And finally, world population data is used to determine the number of people affected locally for each of these cases, and the results of all of the cases are aggregated to determine the total probabilities of various damage levels. So to start with, here we have an overview of the impact risk for today's scenario. It summarizes the main points of what we know about the potential impactor, what regions may be at risk from the impact, what types of hazards and damage levels could occur, and the probabilities of how many people could be affected. So I'll talk about each of these more specifically as we go, but from this snapshot, we can see right off the bat that we are faced with a very challenging scenario here, one that could threaten almost any region of the world, and one that combines a high likelihood of causing no damage with a small chance of causing extremely catastrophic levels of damage. So let's look more at what we're dealing with here. The big first uncertainty is if and where it could impact. As Paul introduced earlier, the orbit is still very uncertain with a 5% probability of striking Earth, and it could be almost anywhere across the globe. These scatter plots here show the atmospheric entry points and conditions from the orbital solutions. The entry parameters vary among the potential points, but they're also well determined by the orbital solution for any given point. So if we know where it's coming down, we know the entry parameters pretty well. The entry velocity range is pretty narrow, between around 15 and 16 kilometers per second, but the entry angle varies significantly from vertical entries near the mid-Atlantic to very shallow skimming entries around the very edges. The entry velocities and angles here affect the altitudes and locations at which the asteroid may airburst or impact and the amount of energy going into the resulting damage. So that's how they affect the assessment results we're going to be showing next. As for the asteroid itself, the potential size and properties still remain very uncertain since we only have initial estimates of its brightness and no real information on the type or density. Could range from a more common stony rubble pile to a much rarer high density iron type object. So taking all those uncertainties into account, we get the size distribution shown here. It could range from a small object around 35 meters across that may pose little threat to a very large object up to around 700 meters, carrying up to 13 gigatons of impact energy. But fortunately for us, we don't just care about the worst case maximums because the amount of risk depends on the probability. So as you can see in the distributions here, the maximum sizes are very large, but they are also very unlikely. The low to mid-size ranges, on the other hand, are much more likely. The average sizes are around 150 meters, 250 megatons, or 9 billion kilograms. The most likely distribution peaks fall even farther below that a little bit, with the averages closer to around 100 meters or 30 megatons or 1 billion kilograms or so. The mass is the main factor that the mission designers will need to determine mitigation options, and the impact energy is the main factor that we use in estimating the damage potential of the various impactors. So now that we have a sense of how much we don't know about our object, we can look at a few different ways of evaluating the threat that it poses. So once we've modeled the damage for all different combinations of asteroid properties and entry points, we can first look at how many people may be affected depending on where the asteroid strikes. These maps here show the average on the left and maximum on the right number of people for each entry point, given the range of asteroid cases. The points on land are local populations affected by ground damage, and the ocean points indicate tsunami damage along the surrounding coasts. Average affected populations range from around 0 to 10 million people across the globe, and the highest average damage occurs around the Nile Delta region in Egypt. Maximum affected populations, on the other hand, range up to 86 million for the worst case, which is around East India, there on the very edge of the impact region. So maps like these give us a good quick sense of the scales of the potential impact consequences if a strike occurs in a particular place. However, we also need to keep in mind how likely the various consequences are. For example, the worst case point in East India happens to be at the very lowest probability skimming edge of the potential impact zone. Impacts in the more likely region that fall around the mid-Atlantic, on the other hand, can only cause notable tsunami damage in the very rare cases of a large impactor. So with that in mind, now let's look at the relative likelihoods of damage from the different impact hazards. This bar chart here shows a breakdown of the relative chance of each type of damage occurring among the Earth impacting cases. The light blue shows each hazard's chance of causing any damage at all, and the dark blue shows its chance of causing the most damage compared to all the other hazards that a given impactor may cause. The table on the bottom also shows the affected population ranges for each of the hazards. So we can see that blast for this scenario is by far the predominant hazard here, both in likelihood and in the affected population numbers. It drives damage in about half of the impact cases, affecting an average of 117,000 people. Thermal damage can also occur in about 16% of cases, but it is almost always less severe and smaller than the accompanying blast. The chance of tsunami is only around 3%, affecting an average of under 1,000 people, but a very large water impact could potentially affect over 1 million people if it occurs near a high population coast. For the size ranges in this scenario, no large-scale global effects are expected, but the potential for intermediate regional environmental effects from the larger end of the size range is still a big unknown. So now looking more specifically at the potential blast damage now, since it drives most of the risk. Here we are showing examples of the range and likelihood of various blast area sizes for a sample entry point near Alexandria. You can see we are faced with a very large range of potential damage sizes. For this location, the smallest quarter of cases are under 40 kilometers in radius. The maximum worst case is around 300 kilometers in radius, and the average is around 90 kilometers. The percentile sizes on the bottom row give the chance that the damage could be smaller than the size shown. So the 75th percentile, for example, you have a 75% chance that the damage radius could be smaller than 140 kilometers, or conversely, a 25% chance that it could be larger. So, given all the damage factors that we've just seen, how do we now consider the overall level of threat in order to figure out what kind of response is warranted for this scenario? So this is where we step back and roll everything together to look at the total population risks for the impact scenario as a whole. These risk probabilities capture the total likelihood of different damage severities, including all the uncertainties in the asteroid properties, impact locations, resulting damage ranges from all the different hazards, and also the overall 5% Earth impact probability. The histogram on the left shows the chance of affecting different ranges of people and shows which ranges are more likely. Again, we see that by far the most likely outcome is a more than 97% chance of no damage occurring at all. All the other ranges are each individually under 1%, but they do include possibilities in the high tens of millions of people. So how do we weigh those two opposing extremes? Rather than comparing the individual damage ranges, we can look at the plot on the right and see how likely it is for the damage to exceed a certain threshold. This plot shows the probability of at least a given number of people or more being affected by the impact damage. For example, there is a 2.6% chance of affecting at least one little person or causing any damage at all, in other words, a 1.3% chance of affecting at least 10,000 people, and only a very small 0.14% chance of affecting over 1 million people. And so finally, rolling all the potential outcomes up into one number, the total average population risk is around 6,000 people, and that's including the 5% Earth impact probability. So wrapping up, here is the summary of the main takeaways about the impact risk. Overall, the object size, potential impact location, and the range of damage are all highly uncertain at this point. The maximum impactor sizes and damage consequences could be very large, but those extremes are also very unlikely. In terms of affected population, the full range could be from 0 to 86 million people among the probabilistic cases that we modeled, and there's an average of around 6,000 people. However, the most likely outcome is still no damage occurring. In terms of the potential hazards, if the object does strike, blast damage is the predominant hazard source with a wide range of potential ground damage sizes and severities. Thermal and tsunami damage are also possible, but much less likely and severe. And although no global scale effects are expected, the potential for sort of more mid-range regional environmental or economic effects still remains unknown. So that's what we know about the risks so far, but threat assessments will continue to be updated as we gain additional information about our hypothetical object. Risk results will be updated as the orbit is refined or as other observations may help narrow down the size or properties. If the impact becomes more likely, then more detailed risk analyses and higher fidelity damage simulations can be performed for critical hazards, locations, or cases. And then these evolving risk results can also be used to support response decisions in several different ways. Firstly, the asteroid property distributions have been provided to mission designers to inform mitigation requirements, and Brent Barbie will be talking more about that tomorrow. Risk assessments can also be performed to evaluate the benefit of proposed mitigation or reconnaissance missions. And finally, damage area probabilities can support preliminary disaster response planning to prepare for potentially large damage within a short warning time. So even though we don't know whether or not the impact will occur yet, they could be very large consequences and we only have 6 months to prepare. So that's where we are with that. And I will leave you with suggesting a little bit more sources to find more information in talks in the impact effects sessions and some of the other sessions. Jesse Dawson has a talk talking more about our asteroid property inference process. And a number of people on our team have talks talking more about our impact effects models and applications to mitigation modeling design. So that's what we have for the risk scenario, given what we know today. So now I will turn it over to Gerhard to introduce Same Page.
Thank you, Lauren. Nicely done.
Thank you.
Yeah, also thanks from my side. Yeah, Romana, if you could start the slide, I can see it very well. Thank you. So I will give a brief introduction to the Space Mission Planning Advisory Group, in short, Same Page. So following a recommendation of the UN Action Team on NEOS, Action Team 14, this group was officially established in 2014. And the purpose of the Same Page is to provide a forum for collaboration on technologies and techniques for an international response to a neo-impact threat. So Same Page is an international technical scientific advisory group. It should present options for neo-mitigation space missions to space agencies and decision makers. Again, I would like to point out Same Page has no decision-making power itself. At present, Same Page has 19 official members, and these are space agencies or space offices, so someone who could contribute to a space mission if required. and 6 permanent observers. So Isa is presently chair of Same Page, and Yuan Uza is the secretariat to Same Page. And an ad hoc working group on legal issues, in short, Same Page Legal Working Group, was officially established in October 2016 because it was realized if you perform a space mitigation mission, there could be some interesting legal questions. Next slide, please. So thresholds and criteria for action were jointly developed by I1 and Same Page. There was a question, when should Same Page get into action and when should we issue some warnings or propose some measures? And the conclusion was what is listed here. Same Page shall start to assess space mission options if an object has an impact probability larger 1% within the next 50 years, and if it's roughly larger than 50 meters in diameter. We heard from Paul's presentation before, it's not always so easy to have a good information on the actual diameter. But if it's roughly larger than 50 meters, Same Page will get into action and assess possibilities of a space mission to mitigate the threat. So if we look at this hypothetical object, 2021 PDC, it meets the threshold criteria because it has an impact probability of 5%, as we know of today, already within 6 months. And the average size estimation is between 80 and 200 meters. So it meets these threshold criteria. And therefore, Same Page will start to assess space mission options for mitigation of this object, 2021 PDC, and results will be presented tomorrow. And in addition, legal aspects related to planetary defense issues in general will also be presented tomorrow, following the presentation of potential options for a space mission mitigation. And I would like to point out that Same Page will assess options. It's not clear that we find a realistic option that anything can be done by a space mission. So in that case, we have just to pass it on to civil protection measures. But we will see what is potentially possible even on this short time notice. And perhaps one concluding remark, so we heard from Paul and Florian, it was always emphasized that this object 2021 PDC is just a hypothetical object, a hypothetical threat. But I1 and Same Page are real groups, they do exist. Thank you.
Thank you, Gerhard, and thank the presenters. And again, you'll hear more from these individuals as we go forward with the exercise. I just want to give a bit of historical context. Back in 2004, at the first Planetary Defense Conference, we actually found that there was no formal process for looking at a threat and providing a warning to leadership as to that a threat existed. And so we've come a long way. I think the work that the United Nations has done in setting up a Same Page and I1 have kind of formalized a process of how you would actually present an actual threat and how it would work its way up the leadership chain. This afternoon, or soon we'll be hearing a panel session, which will go into a little bit of depth. And one of the objectives of the panel session is to present, they have heard these presentations, and the panel members have, and they will be asking questions as what should we be doing now? What notice should go out now relative to this particular threat? And I think from those out in the that haven't seen these kind of things before, the kind of questions you should be asking is, what would my impressions be now, given this information that you probably will see in the press, or would certainly see in the press? What would your thoughts be? What should we be doing? And so the purpose of the exercise is to acquaint basically anybody who might be involved, and we all would be, as the type of this type of threat, how it would emerge, how options would be considered, what options would be available, and so forth. So, as I said, Romana Kaffer will be leading a panel, and she'll introduce the individuals on that shortly. So I guess we'll go for a break now, and we'll begin precisely at the half hour. So.
So allow me to introduce the panelists. We have Director of the United Nations Office for Outer Space Affairs, Simonetta di Pippo. In this position, she leads strategic policy and programmatic activities and advising the UN Secretary General on Space Affairs. And she served as a Director of Human Spaceflight at the European Space Agency. She's also an academician of IAA and UN International Gender Champion. And as you have heard, she has assigned the name Di Pippo to asteroid 21887. So welcome, Director Di Pippo. Then I have with us Martin Esurki. Martin Esurki is the former spokesperson to the UN Secretary General. He is currently the Director of the United Nations Information Service in Vienna. Before that, he had an extensive journalistic career at Thomson Reuters, serving as bureau chief, news and television, both in Moscow and Seoul. And his prior postings include also assignments in London, East Berlin, and The Hague. Martin is a UK national and a graduate of Bath University, European Studies, German and Russian. Then I have with me Kelly Fast, the ION coordinator and Nearest Objects Observation Program Manager at the NASA Planetary Defense Coordination Office. Kelly Fast coordinates the meetings of the ION Steering Committee and is the Nearest Objects Observation Program Manager. She has a degree in astrophysics from UCLA and a doctorate in astronomy. And she is also one of the panelists who has the main belt asteroid 115434 renamed Kelly Fast in honor of her contributions to planetary science. Gerhard Rollshagen is one of the PDC co-chairs, but he's also the chair of SamePage with a doctorate degree in physics from the University of Göttingen and a postdoc at the Los Alamos National Laboratory. He joined the European Space Agency at its research center ESTEC in Noordwijk, the Netherlands, as a senior analyst in the Space Environments and Effects section. Since 2009, he was also co-manager of Nearest Object segment of ESA's Space Situational Awareness Program, which is the predecessor to ESA's Planetary Defense Office. He's the chair of SamePage since 2014, so since the establishment of SamePage. And he also is was given an asteroid 332733 named Rollshagen after him to honor Gerhard as a driving force of the European NEO program. Then we have heard presentations by the two experts, Lorian Wheeler at the NASA Ames Research Center. She's the risk assessment lead there. Her primary work includes developing physics-based probabilistic models of asteroid entry and damage to evaluate the risks posed by potential impact threats. And of course, last but not least, we have Director of NASA Center for Nearest Object Studies at CNEOS, Paul Chodas. Now, we have introduced Bill Ayler already at the beginning as one of the core forces of the Planetary Defense Conferences, in fact, as the initiator of this conference. He is a technical fellow at the Aerospace Corporation Center for Orbital and Re-entry Debris Studies, and he initiated these conferences. He served also on the action team on nearest objects, established by the UN Committee on the Peaceful Use of Outer Space, and that then led in 2014 to the establishment of SamePage and ION. So with that introduction, and I thought the panelists deserved a really more extensive introduction because we usually jump to substantive matters immediately. So I would like first to ask Kelly Fast as ION coordinator. We have heard the presentations, the estimates of this hypothetical impact threat. And I would like to know from the ION perspective, what would be the next steps? So we heard that the probability was low, lower than 5%. However, in accordance with the initially agreed criteria and thresholds by ION and SamePage, this is already enough for ION and SamePage to take some action. So please, Kelly.
Sure. As mentioned earlier, because that probability has broken that 1% threshold that ION and SamePage have set as the notification threshold, and this is an object of a size that would pose a threat to Earth, not just some very small asteroid that would create a pretty fireball, but something that could pose a threat. The ION Steering Committee would pass information along to the UN Office of Outer Space Affairs in a notification format with the details like what Paul rolled up. And ION, as a collaboration of signatories, would continue its nightly operations. It's what it does all the time anyway, and continue observations, but it would focus on this particular object, as it always does. If there are objects of interest, observers will coordinate and try to gather additional data while the object is observable. And that will be the case here. As Paul presented, there is uncertainty, and that's why we have this low percentage, but not zero, not 100%. And it's because more data are needed. And so to the extent that observations are possible, the ION community will continue to observe the object, try to gather more position information in order to help Paul and his team narrow that impact possible position, where the asteroid is in space, continue to redo calculations, and then for Lorian and her team to continue to do the modeling, and so to hopefully try to narrow that and get any other information that is needed for others to make decisions and continue their modeling.
Thank you very much, Kelly. So just a quick follow-up question. As we know, we speak different languages, right? So there is the language of the technical experts, and then there is the language of the decision makers. So we're very glad that actually this Planetary Defense Conference is in conjunction with the session of the Scientific and Technical Subcommittee of the UN Committee on the Peaceful Use of Outer Space. And both ION and SamePage report to a Scientific and Technical Subcommittee regularly on an annual basis on their progress. So my question would be, when ION, for example, would tailor the language with such information, how do you translate this technical information into a language that would also be understandable to decision makers?
Well, that's a very good point, and something that has been discussed at these conferences and in other exercises, and that is an important goal, is to try to avoid the jargon where possible and to boil it down to the facts in units and terminology that is as widely understood as possible. And it can be difficult because certainly we know that decision makers don't like to have to work with uncertainties and probabilities, but to at least minimize that as much as possible and try to explain it in like what Paul showed earlier with diagrams showing in space what this means, or what Lorian presented earlier with graphics to try to illustrate, the point. It is true we need to find a common language and to try to stay away from the community-specific jargon as much as possible to make it into general terms that decision makers and the public can understand.
Yes, and then in parallel, when we saw your diagram presented at the first exercise, the ION and SamePage obviously have close linkages and would establish in parallel the communication on that. So Gerhard, you're the chair of SamePage. You have been briefed now on all the available parameters of this asteroid. What would be the SamePage sort of first reaction? You've pointed out that the SamePage will start to assess space mission mitigation options, but what do you think in terms of timelines what would that entail?
Yeah, obviously, this is a very challenging case. So in previous cases, when we tried to analyze something as an exercise, there were years of time. And this is also a realistic timeline if you know about space missions and launching capabilities. But here we have a hypothetical threat, and this is absolutely not unrealistic, where we have half a year, 6 months time. So we will assess what is possible with a space mission. And the answer could well be, oh, sorry, but there is nothing really what we can do. I mean, we will look at various options that could have to do with a space mission. One is a deflection. Yeah, the time might be too short. We could look at a destruction. Perhaps that is a possibility, if that is the only technical option. But also, if that is not found feasible, perhaps it's possible to send a very small, fast flyby spacecraft to gain additional information. Because if we could refine the size uncertainty, where we heard there is still a large uncertainty, that would help civil protection measures. So same page will just get into action and see what could be done and give a recommendation. Again, it is also possible that we come to the conclusion, in this case, it's not much we can do with a space mission, but we will see what would be possible. And of course, we will stay in close contact with I1. And whenever they have better information, we expect them that we receive them very quickly, specifically if it's on the size of the object. But in principle, for us, we look if the impact probability is larger than 1%, and whether it's 5 or 10 or even 100, we will see what could be done by a space mission.
Thank you. And now I would like to give the floor to UNUSA Director. She serves as an advisor to Secretary General on space matters. So obviously she would be the first point of contact when it comes to such an issue, especially if a hypothetical impact could possibly, be a danger to all humankind. Director Pippo, I see you on the. Yes, I see you well. What would be your channel of communication and your advice? Obviously, one side would be for the Office for Outer Space Affairs to make available this information to UN member states. And now the General Assembly has given us the mandate that in case of an impact hazard, all member states, in particular those who do not have the capability in this area, to be properly informed. Please let us know what would be your steps in such a case. Thank you.
No, thank you, Romana, and thank you very much for this opportunities. It's quite an interesting exercise, by the way, and I shared the view with all the other panelists that even if it's an hypothetical scenario, it's still extremely helpful in understanding which kind of steps we should take in case this happens. Indeed, the Office for Outer Space Affairs has a lot of different mandates. And in the specific field is exactly what Romana just said. So we got the mandate to disseminate information, and in particular, as we do in most of the other cases or the other topics we deal with, we are particularly focusing on emerging and developing countries to help them in acquiring capabilities, but also eventually to get informed and to get supported in cases in which they don't have the skills in the technologies at home to deal with a certain topic. So, and in this case, we will have exactly the same approach, because you have to consider that the Office for Outer Space Affairs is a sort of a gateway for space in the UN system. And in particular, this is even more true since now a little bit more than 1 year, because we changed status inside the UN system. And indeed, as Romana was saying, starting from the beginning of last year, The director of the office is also officially the UN Senior Advisor of the Secretary General on Outer Space Affairs. Well, I believe that what Gerard just said, and also Kelly, it's extremely important that we coordinate all the efforts possible, and this is exactly the spirit of IO1 in and same page. And also Gerard was very clear. I mean, 6 months is quite a short time to put together a mission, and we know that quite well. However, it's also true that if for whatever reason we will have a situation in which an asteroid could be really a threat for Earth, then we need to put all the efforts together. So we need a sort of a strong coordination mechanism. And so this exercise and the fact that we are involved with the top level space agencies in the world and other organizations is a very good sign of the fact that we really intend to do the best we can all together collectively to reach this goal. Now, what we can do for sure is to disseminate information, to be in strong contact with IO1 and same page. But I always advocate, not only in this field, but also when we talk about disaster management, for example, with our SPIDER program, that we really gain more and more, let's say, an operational service, because, or at least that we are recognized more and more as the entity which can help member states, again, in particular emerging and developing countries, but not only, when there is a disaster ongoing, through a coordinated global mechanism. And in fact, for example, the UN SPIDER program developed this network of regional support offices, and the network is growing and growing. In the last few years, it's been really increasing a lot in terms of number of centers. And these are national centers managed at national level, but embedded in a network which helps a lot in coordinating activities, and also sharing information, sharing lessons learned, sharing best practices. And I believe this is extremely important also in the field that we are discussing today, planetary defense. But it's also true that, as Gerard was saying, the most difficult part at a certain point in time will be to put together a mission able to save the Earth. So the effort is absolutely key for the future. And what I would advocate for is that we collectively discuss the best mechanism. And so this exercise is exactly that, the best mechanism that we should put in place in order to allow us to do our job properly in support of humanity.
Oh, Ramana, let me just ask a question. You know, I'm going to play the role of a member of the public here, and I live in California, and I live by the ocean there. So if it hits in the ocean there, that's going to be a problem for me. And how worried should I be? I mean, is this something that am I going to get good information on this? And if so, how would I get that?
Thank you, Bill. Who would you address this question to? Probably to...
Well, I'm just wondering, does the United Nations, for example, have a process for disseminating information to the public, and how would that work?
Which gives me...
Go ahead, please.
Yes, which gives me the pleasure.
We have different mechanisms depending on the topic. For example, if there is a space object supposed to re-enter the atmosphere, which is, let's say, big enough to potentially create some problems, well, we usually deal, we establish contacts, we always have contacts, but we establish daily, if not every hour, contacts with the space agency in charge. And so we disseminate information to all member states of COPOS for the time being. We did, for example, this quite an interesting process, because we stimulated a lot in particular CMSA, the China Manned Space Agency, when they had Tiangong coming down. This is, in that case, it was done in a proactive manner. So we really established a continuous contact. Also because clearly there was a wonderful website that they had to keep informed the public on a continuous basis. Most of the information were in Chinese, so we had also to work a lot with them to get some information on a I don't want to say daily basis, but weekly basis. And then when we get closer and closer, we got a lot of information that we disseminated to member states. When we talk about disaster management, well, the SPIDER program is quite established. That started the operations in 2006. We are part of the Charter on Space and Major Disasters. We are also strongly linked with the UN Disaster Risk Reduction. It's an office of the Secretariat dealing with disasters in general. And we have also contacts with other organizations, national and international, which can help in this process of acquiring information. And we have a portal, we have a knowledge portal, which is free for everyone, where we put all the information, sometimes even images that we obtain, also sometimes high resolution radar, etc., of the area impacted by the disaster, etc., etc. Clearly, we can also trigger the charter, for example, on behalf of UN entities or on behalf of governments. So there are a lot of different mechanisms. But what I was trying to say before is that really we probably need to work together to find even a more effective mechanism, even a more effective, let's say, procedure that we should be able to follow, and all in agreement, even if at the very end be the UN doing it, but all in agreement, so that we can pass information to all member states in a coordinated manner. Because we know well, as like when you have a tsunami or you have an earthquake, it's not just a nation, it's not just a country which is affected. So you need to have a sort of coordination also in disseminating information. Again, I really welcome this exercise, because I believe it's a first step, not the first step, but a solid step towards creating such a mechanism.
Thank you very much. And I also had a question for Paul Chodas, if I may. Paul, you know, you presented this thread, and it sounds like it's, you know, this one is it's a made-up thread. How real is this? I mean, I hear people saying that, you know, I don't really need to worry about this. This is not going to happen anytime soon, and we really don't have anything to worry about. Could you explain why this, if this is something that's actually realistic, that might happen in a reasonable, that we, you know, we might not see or might see?
Yes, thank you for that, Bill. Yes, this is realistic. Asteroids of this intrinsic magnitude we haven't discovered them all. I mean, we haven't even found half of them or so at the 140 meter or so size, and smaller even. So, and the orbit is realistic. So this could very well happen, yes. We've intentionally made this particular exercise have a very short warning of only 6 months to kind of call attention to the disaster management that might result. And of course, we have a very large potential impact region. So you know, most countries in the world right now are at risk. As the impact region shrinks, there will still be multiple countries at risk for a long time. So we will need United Nations coordination on messaging, and especially in how to handle disaster response across, you know, many countries. And I think that's very realistic. And if I may add also, we need international cooperation and coordination on observations, because in this case, we'll need large telescopes. to observe this asteroid. That's how we get more information on its chances of impact and where it could hit. So coordination, international coordination on getting the biggest telescopes in the world would also be needed. And finally, communicating information to the public will always be a challenge. And events over the last few years have shown that finding trusted sources of information and emphasizing which sources of information are to be trusted is another area where we'll need an international collaboration and coordination to make sure that we can establish those communications channels to the public.
Mm-hmm. Thank you.
Thank you. And this brings me actually, when we talk about communications, we have an expert here on communications. Martin Iserki is the UN Director of UN Information Service, but he's also a former spokesperson to the Secretary General. Martin, you have been involved in a lot of emergencies in your service as the spokesperson to the UNSG. So it would be really interesting to hear from you the parallels that can be drawn, and what does such an emergency entail when you come to the highest level of communication, not only to the media but also then to the public, as Bill mentioned. How do you appease them in terms of not getting into a panic mode? So please, the floor is yours.
Well, thank you very much indeed. And I don't have an asteroid named after me, and I didn't win an Oscar yesterday. But here I am. And yeah, actually, probably, yes, I was the spokesperson for the spokesman for the Secretary General. And yes, also I was a journalist for many years. So if you like, covering the story and knowing what information I would need and my team would need, and that included disasters of the kind that one gets in countries like the Russian Federation, which is very large. And because I'm a former journalist, I have a heck of a list of questions. But first of all, I wanted to come at this, as you said, Romana. Yes, there's an upward chain of information that would be coming from Iwan and Same Page, and Simonetta would be relaying this to the Secretary General. I would imagine that the Secretary General would be bringing together the Chief Executives Board, which is, if you like, his. It's the head of all of the heads of all of the different organizations within the UN system. So, for example, the Refugee Agency, and I think they would be quite busy, the UN Development Programme, UNICEF, the Children's Fund. So all of these would need to get together. They all have communications themselves. So even just looking at it from the UN perspective, there would be many voices. And so this brings me to a communications parallel that, of course, we've had in the last year. Very different threats, but very similar in the way that it would involve different bits of the UN system and the whole world. In other words, national governments, regional organizations, and of course, I'm talking about the pandemic. So in a sense, if you're thinking about, to answer Bill's question, you don't want your beautiful house on the beach washed away in California, or if so, when's it going to happen? Who's going to be the Dr. Tedros? Who is going to be the person who is out there, probably every day, briefing people, giving them, as you said, Paul, the trusted information that you need? We've seen the spread of misinformation during this pandemic, whether it's the conspiracy theories about COVID-19, does it exist at all, right up today to anti-vaxxers, vaccine hesitation, and so on. So you need a common voice who can speak on behalf of the system, if you like. And then the other part that I wanted to address was what Simonetta mentioned about the coordination and a stronger global coordination. And I have some questions there myself that would be crucial to know as a communicator. And that is, what is the decision-making process? Gerhard mentioned that the recommendations would be made, but to whom? And how would those decisions be taken? Corpus is not all 193 member states. What role would the Security Council have? And so on. So that would be, for communicators, that would be crucial to know. And also, you know, is there, in addition to the Dr. Tedros, the institutional figure, you know, who else is there who would be a reassuring voice, or perhaps later on not so reassuring, but there's a clear need for voices in different languages who would be credible. And this comes back to what I was saying about what we've seen in this pandemic and what would need to happen. Kelly made a very important point. The data's already there. Even before IWAN notifies the member states through the UN Office for Outer Space Affairs, it'll be all over the papers. In a sense, you've already lost the narrative. How do you get it back? So these are very, and I know that you have discussed this many times in previous exercises and conferences, I know, but as it's coming to this fresh now, those are some of the thoughts that I would have.
May I?
Yeah, also.
If I may comment just on the observation part, as you mentioned, the news will be out there before IWAN or any of the signatories or any of the observers really have anything to say about it. And that's what happens now with everything. So it's just the world that we're operating in. And so that's why it's better to get the right information together and then come out with it rather than rushing, because we're not going to be first anyway. And you mentioned about having the faces, the voices, and in addition to IWAN as a collaboration, sending information through the steering committee to the UN Office of Outer Space Affairs. All of those individual IWAN signatories, NASA, ESA, individual observatories in different countries, other organizations, they'll be working in their own countries and doing what they always do and through their communication avenues, and also being those additional expert voices within their own countries. And so that in addition to that collaborative IWAN messaging will help to get the right information out there. As you said, the data are public, but it's also that explaining the data and the interpretation and everything, and as was mentioned earlier, putting it into language that the public can understand. But it will be a group effort around the world, and hopefully IWAN signatories will be a part of that.
I think you made a really good point in that
You're muted.
went the wrong way on the button. I think you make a very good point about having a path for reliable information. And I just want to say that I think a number of agencies have actually developed some really good web pages. CNEOS, for example, has an excellent page providing the facts on everything we know about asteroids and such. And so I think that there are paths. And again, going back to 2004, there was none of this. There was no web page that had reliable information in it that was, you know, the public could go to see what the truth is. And I think there now is such a thing, and I think that's really very good.
Yes, and if I may, Martin, you pointed out one aspect, communicating, also, but then also decision making, right? Who would be the end decision maker? And since you have been at the Security Council, I mean, at the, working with the Secretary General, and you know that under the Charter, a threat to international peace and security is always brought to the Security Council. In case of a hypothetical asteroid impact that would be a hazard to all the planet, what, in your view, would be the process for the Security Council to actually meet and address such an impact hazard?
Well, I would also defer to Simonetta, who will know, as I'm sure you do, what the chain would be within the system, given the Secretary General's role. He can invoke Article 99 of the Charter to bring something to the attention of the Security Council. So that would be one mechanism. You would think, given the permanent 5 are all involved in space in some shape or form, this would mean that their focus would be quite sharp at this point. So one would assume they would not need so much persuading. However, of course, what we've seen in other areas, whether it's on Syria, whether it's on Yemen, whether it's on Myanmar, that there's plenty of leeway for a drawn-out process in making decisions when you don't have the time to do that. Yeah, the Secretary General may need to bring it formally. It may be that the permanent 5 act on it as soon as they hear from through Corpus, the official line, if you like, from the experts in I1 and from same page. Yeah.
So a brief question also to Director Pippo on this. We have, if we look at the global agendas, the Agenda 2030 for Sustainable Development, the Paris Agreement on Climate Change, and also the Standard Framework for Disaster Risk Reduction, space has obviously become a very integral part of these global agendas, and there are parallels. So in terms of positioning, our office and also the space agenda at these high levels, I would like to hear from you your views in terms of being an advisor to Secretary General, how this would be dealt when it comes to really, bringing this before decision makers.
Well, indeed, this is in fact something extremely important also with respect to what was just said. So the fact that data have to be certified, that we had, for example, the experience of the pandemic, where we in a way did collectively in the UN and a huge put in place a huge effort in really trying to provide the real news. I try to be diplomatic here, and to be in contrast with the fake news. You see what I mean? Which, as Bill was saying, were around all over the place. And in my point on climate change, on disaster management, is that space needs really to be at the center. It needs to be recognized by policy and decision makers at the center. One of the examples that I also always make is if you look, for example, in the climate environment, in the climate crisis environment, we always talk about essential climate variables, the 54 essential climate variables as defined by CEOs, okay? And we know that more than half can only be monitored from space. But if you go to a normal summit or a normal conference on climate, well, space is there. There are a couple of presentations, but it's in a corner. So we really need, and that's my job in a way, but I believe it's a collective advocacy, let's say, effort, in trying to always demonstrate that the data that we collect from space are certified, reliable, and in most cases are the only data that we can trust in order to put in place certain actions. In the case of climate, is mitigation, adaptation, but it's also to try to really understand and make a simulation of what can happen in the future due to the current situation with the various variables. Now, in our specific case, I believe that there are a lot of avenues that we have to deal with in parallel. There is a technical, let's say, path where we have really collectively to decide which kind of missions we could put in place if there is a real threat. And indeed, we know, or we all know, that it's not so easy to put in place a mission in 6 months, launch it, and reach a place. So it's really quite let's say demanding or challenging, whatever. The fact that we do need to put together information which are reliable, where the public, but not only the public, can really look at with confidence. There is a need of a crisis communication plan. There is a need of coordination of the various civil protection entities. But I believe that what has been done with IO1 and SamePage is a top level. We put in place, in a way, a top level mechanism, which can help, can strongly help, let me put it like that, the decision-making process in terms of, let's say, leadership of the world through the 5P, the Security Piso, the Security Council, but also it's a mechanism which can technically, from the technical perspective, from the substantive perspective, can help the system to put in place the best communication plan possible, and also all the mitigation and adaptation measures. Now, what I'm trying to say is that we are not at the end of the process. If I may, we are just at the beginning. Bill was mentioning this website, this repository with all the information, which was not there before. It's a big step ahead. The coordination between organizations and space agencies, a big step ahead. The fact that we are doing today this exercise, I mean, this week, but also that today we are debating this, is a big step ahead. The fact that we are also involving already journalists, spokesperson, etc., is a big step ahead. But again, we are at the very beginning. And so I believe that the positive side, if I may, is that we really have the best minds and the best skills all together right now, thanks to IO1 and SamePage. And if I may, also the UN can help a lot in this process. And so we can mutually coordinate and provide the best service possible to member states.
Thank you very much. I would like to take now some questions from Q&A. For example, is it possible to think of an international charter involving observatories and astronomical satellites for this kind of emergencies? This is a really interesting parallel because we have, for example, international charter space and major disasters, by which, for example, the space agency offer for free to countries that were hit by disaster and don't have capacities to those data. So Kelly, what do you think about this proposal or question?
Not sure I fully understand it, but in a sense already you have the signatories to IWAN already contributing their assets for this purpose. And certainly if something is discovered with such an impact probability and is going to be so newsworthy, you will have IWAN signatories and non-signatories contributing their observational assets. And also all of the observations, the position observations, do go to the Minor Planet Center, which is the International Astronomical Union recognized repository for such information. So all of those data go there and are available to the world to use. And then there's additional observations. It's something we look at actually as part of the IWAN observing campaigns, observations that study physical characteristics of objects. Normally that might be more of an academic pursuit and processed on an academic timeline, and we're trying to develop ways to make it processed more on an operational timeline in a situation like this where information is needed rapidly. So all of that already operates, but as to if there's an additional measure beyond this collaboration that is IWAN and the internationally recognized public databases that are already available. I'm not sure what the other possibilities are, but should be interesting to discuss.
Yeah, thank you. And I know that, this year you've reported that actually it was the highest number of asteroids that were discovered, around 3,000 new asteroids, despite the pandemic. So the network is there. Obviously, you are always, as an ION coordinator, inviting worldwide observatories to join these global efforts, which is really important because observations as part of this recommendation, of course, are the first pillar. Then is the mission planning, and the third is the disaster preparedness. And I have here a question from disaster management community, which is where would be a place for disaster management to go to for science of this? Do we call a UN or ION, or do you expect that each space agency would provide that information? Who would like to answer this or take on this? I know it's part of the ION as well, ION sort of statement of intent.
You mean just providing the information that is developed by observers and modelers? But
perhaps Lorian, perhaps Lorian can present, since you were also dealing with presenting the actual impact probabilities and what parts of the Earth would be hit, and also the population numbers. So maybe Lorian, could you please take the floor on this?
Yeah, so I can't comment on what the chain of communication would be, but we work under NASA's Planetary Defense Coordination Office, so all the information that we produce would go up and out through there. But in terms of disaster response, we can produce things like geographic shapefiles of damage reasons, or these probabilistic estimates that can support preliminary disaster response planning. And then individual agencies can take that information and apply it to their local areas to do things like more specific infrastructure assessment, or use that information however they think fits their threat tolerance and the level of risk that they feel they're at.
Romano, may I ask a question real quick?
Please.
Lorian, I had a question too, and this is something that came in one of the chat messages, and the question was, what would happen to the world economy after the announcement? Do you look at that? And for example, if somebody's planning to buy a house, should they wait?
Yeah, so looking at the larger economic factors is not something that we currently have a model for. We tend to sort of boil everything down into the population numbers. And then, things like insurance companies have plenty of formulas for turning people into dollars. So, what happens in the market, it's not my area of expertise, but there's certainly information there that could be gained, and we're working towards involving more infrastructure assessment and things like that would start looking at that sort of thing. And I know Tim Titus has a talk in one of the sessions on sort of some of the more longer term downstream effects that might be possible for sort of a mid-scale impactor that's not quite global climatic effects, but could have larger sort of environmental subsequent events.
Mm-hmm. And also, given your charts, you basically said that right now, it's the likelihood that anybody will be injured is like what 3% or something like that, and so should people, the risk is worldwide. So should anybody really care, or just go about their business right now?
Well, so I mean, that's the conundrum, right? You have the potential for a lot of consequences, and right now, given the 5% Earth impact probability, and that only then half of the 5% that impact Earth cause damage because they may be small, or they may impact over, somewhere low population and be kind of benign. What do you do with that information? And different agencies in different countries may have different tolerance levels for handling that sort of information, which is why we sort of try to provide the gamut. And then decision makers can take that information and decide, well, where's my where's my risk limit? How much, what's the comparison of the money I would spend on mitigation versus what I think this risk is? So decisions can sort of go forward from there.
Thanks.
I may add something here, Bill and Lorian. I think there would be, in view of the drastic consequences of an impact, I think there would be a demand of why can't we increase this impact probability? Why can't we be certain if it's going to hit or if it's not going to hit? And so there's so there would be a communications issue on our part to explain that the asteroid's too far away. We can't figure out for sure until we get more observations whether or not it will hit. And this period of uncertainty will cause perhaps a lot of distrust, frankly, of the technical experts as we try to explain, our level of uncertainty and the fact that we'd be doing our best to try to decide, to figure out whether it's going to hit or not. So communications would be a big issue, I think.
Absolutely.
Thank you.
I think, Director Pippo, you have your hands raised. Would you like to add something to this?
Yeah, in reality, it was from before, but just to say that I share all what was said, and again, I really believe we are just at the beginning of this path. Even if we did a lot already, you did a lot, and we did a lot collectively. But again, there are a lot of let's say activities, actions that we have to analyze, that we have probably to establish the precise procedure on who has to do what, how to alert the national civil protection entities. And in this case, we can also try to leverage from the experience and expertise we have through the UN SPIDER regional support offices. I agree with Kelly that we have already a very good repository of information and a very good network. So the charter in this specific case, say a charter type as a mechanism probably is not the best, because in this case we have to consider potential impact on a global scale, which hopefully is less of a probability in the case of a natural disaster, even if, yeah, also in that case there are potential issues on a global scale. Again, I would like to underline that we should make reference, at least in terms of lesson learned with the pandemic, because the pandemic helped a lot the world to understand where we are fragile and where we are weak in terms of coordination mechanisms. And the question is, do we have in place all the mechanisms that could help in reducing the number of casualties in case of a disaster, in this case, in case of an impact? Well, that's, in my opinion, the main question. And if you look at the pandemic situation, probably with this question mark in mind since the very beginning, I make an attempt of saying that probably the situation could have been handled better. But it was the first pandemic. I hope it's the last one. But still, it's let's say a sort of a test bench for other potential impacts that threats that we have to treat on a global scale. So again, we are in a very good configuration. We did already a lot, but in my opinion, there is still a lot to be done. But as I said, we have all the skills and the best minds there in this field. So I'm quite confident that we will do it soon and in the best way possible.
So I would thank you very much. I would also like to ask Gerhard, being the chair of Space Mission Plan Advisory Group. Obviously, same page comprises space agencies, and they participate on a voluntary basis. Now, in case there would be a need to plan a mission, a space mission, In terms of resources, how do you see this coming together? Would that be a coalition of the willing? As we all know, these are not inexpensive matters. What is your view on this?
Well, of course, we don't really have experience how this would work out. So Same Page is first of all a technical group. So we would look what would be technically possible. And it might involve saying, okay, we need an existing launcher from this space agency plus 2 others from that agency where we know the capabilities. So some coordination will be required, and we might come to the conclusion only if we coordinate and cooperate, it's possible to do something. So this will be then a technical coordination and clearly some result of the assessment. How this is realized in practice, or if it's been realized, that is another question. Also, there could be different options, for example, to take a higher risk option to deflect the object with a higher probability, or if something goes wrong, to have more margin. So there will be various technical options presented, and it was already mentioned before, the decision to act is an open question still. And also, how can the coordination be achieved on a short notice? So we realize we will look at technical options. What is technically feasible with existing technologies or with something that can be developed on a short notice? So there was one question, could you station something already in orbit to go there faster, or related is something to have all equipment ready on the ground to launch it quicker? All these are technical possibilities that will be considered. But the decision to act and what has to be done, this is still an open question. Actually, we realized when we discussed various options, there are many open questions which we still have to answer. But I think I1 and Same Page are a very good first step to address these issues.
Thank you. And I would like to wrap up this with one final question, and actually to Martin Asurki, because we would like to appease everyone. Anyway, this is a hypothetical impact threat scenario. And there is a question of how would you try to avoid panic if the UN member states receive the information that the asteroid is supposed to impact in only 6 months? Martin, the floor is yours.
Yeah, it's not really a good answer to that, is there? I mean, I think that different people have said at various points during this discussion, which I found fascinating and jaw-droppingly worrying in many respects, because a lot of the bits are not in place despite the work that has been done. Really great work with the 2 groups that have been set up just since 2014. That's incredible. But not knowing how the decision would be taken, that's quite nerve-wracking, I would say, for you guys and for the general public, if that's generally known. So the answer is it's really, really difficult and almost impossible if the news is already out there. And you're quite right, Kelly, that you need to make sure that you are providing the certified, clear scientific data and information that people can rely on. But in the meantime, the story's out there. And yes, I saw something in the chat. People will be booking flights to Australia and New Zealand. You know, I'm not kidding, the refugee agency would be very quickly overwhelmed. UNICEF would be overwhelmed. World Food Programme, people would be moving, they don't have food. You could have conflicts erupting because of people trying to cross borders. So the idea that you can somehow calm panic, yes, there would be the need to do so, but that's why I think this idea of which will need to come from member states, of course, but the idea of an awareness raising beyond this annual International Asteroid Day, which I think is a great idea, to have something that's longer range that can really build up not just awareness, but so that people start to ask those questions. So moving the dial from people being concerned to then saying to their elected representatives, what are you guys doing about this? Where's the plan? And that will presumably provide some additional outside pressure, if you like, to the governments to really look at this in a way that goes beyond what's already happening. And this is not to say that things are not happening at the moment, of course.
Thank you very much. And of course, we know that many member states have already have their action plans and preparedness plans on board and have incorporated NEOS as part of their preparedness campaign. So to go back to this question from the disaster management community, it's at this point, I think we are at the sharing of the best practices, and it's work in progress. Yeah, so with this, I think we have had a really interesting discussion and covered many aspects. I'm really glad that you could all join and really provide inputs from your perspective, considering your careers, current and past. Bill, would you like to add something to wrap up?
Yeah, I would. And I think this has been really interesting. And every time we do these, we raise a number of issues. And I just want to make everyone aware that later in this conference, we'll have disaster managers and disaster responders involved in discussions. And potentially, as was said, having some kind of a plan where the public has confidence that we can handle a disaster like this in an organized way may prevent people flying to different parts of the world, for example. So in any event, people should look forward to that. And I think we are now going to go to a break. And after the break, we'll hear something about the DART mission. That's the Double Asteroid Redirection Test. That's one where some people are worried about, can we move an asteroid? We'll find out. So that'll be an interesting mission to hear about. See you in 15 minutes.
Welcome to session 3 of the PDC, the DART topical session. My name is Dawn Graninger. I'm from the Johns Hopkins University Applied Physics Lab, and I'll be serving sort of as one of your virtual hosts today for the next hour, along with Andy Rivkin. So today we will be having 5 live speakers during this hour. But as a reminder, please check out the different e-lightning talks and posters that are available on the conference website, since there's so many of them that are relevant to DART. Additionally, could you please place any of your questions in the Q&A window within WebEx? So for about the last 15 minutes or so, we'll have a live Q&A session with all of our presenters, but we will be handling those questions at the end of the session once all of our speakers have presented. So we'll dive right in. First up, we have Dr. Thomas Statler from NASA headquarters, and he is the DART program scientist, and he'll be presenting an overview of the DART mission for the next 10 minutes. Take it away, Dr. Statler.
Thank you, Dawn.
Sorry, I was just going to say I was going to give speakers a notice 2 minutes before their time is up. So if I bust in to say 2 minutes, that's what that is.
Thanks, Dawn and Andy. How's my audio? Can you hear me okay? Okay, fantastic. So we are 7 months away from the launch of DART and 29 months away from the public release of the final DART data set and the end of the mission. So it's going to be a very exciting 2.5 years coming up, and I think a very quick 2.5 years, especially for the team. Next slide, please. So to start with a little bit of context and step back for a moment, DART is the first flight mission developed under NASA's Planetary Defense Program, which is operated in the Planetary Defense Coordination Office, or PDCO. PDCO was established at NASA headquarters about 5 years ago. It manages planetary defense-related activities across NASA. It coordinates with U.S. interagency and international efforts in planetary defense. And in the mission statement you see on the slide is to lead national and international efforts to detect potential for significant impact on Earth, to appraise the range of potential effects by impact, and to develop strategies to mitigate those effects. Next slide, please. Planetary defense encompasses a broad range of activities, starting on the right side of the diagram, to search, detect, and track near-Earth objects and characterize them using ground-based and space-based telescopic assets, Those data are compiled, managed and archived, and orbits are computed by the Minor Planet Center at the top of the diagram. And in the upper left, those data are also used to assess the impact risk by the Center for Near Earth Object Studies. Down at the bottom of the diagram, you can see how PDC also is involved in interagency and international coordination through groups, many of which we heard about in the last session. And finally, on the lower left part of the diagram is the mitigation activities in planetary defense, both in terms of emergency response and in terms of actual mitigation of the impact risk. Next, please. And of course, DART lives in that part of the diagram. DART is the first full-scale flight demonstration of an asteroid deflection technology, namely the kinetic impactor. Next, please. Now, this is all part of a larger strategy. In the US, there is a national near-Earth object preparedness strategy and action plan that was put together by an interagency working group under the auspices of the Executive Office of the President. And it has 5 goals. First, to improve NEO detection, tracking, and characterization. To improve NEO modeling, information, and integration. Goal 3, NEO deflection and disruption mitigation. To increase international cooperation and to strengthen and exercise impact protocols. And the DART mission obviously flows from the third of those goals as a demonstration of a mitigation technique, a deflection technique. But it's also directly relevant to goal number 2, because the results of the DART mission will give us a tremendous amount of new information on the properties, the physical properties of NEOs and our ability to model those properties. And it also has implications for goal number 4, to increase international cooperation. Next slide, please. Because as we heard from Patrick Michel and Michael Coopers earlier today, DART also is part of the AIDA international collaboration, the Asteroid Impact Deflection Assessment collaboration. I won't go through this slide again because it was already spoken to twice, but just to remind you, the gist of it is at the bottom of the diagram, that the DART mission, as the first demonstration of an actual asteroid deflection technology, together with the ride-along CubeSat coming from the Italian Space Agency, which we'll talk about later, that mission sets the stage for the science that will be conducted by the HERA mission that will really enlarge our understanding of a planetary defense technique and also asteroid science. Next, please. So DART is the double asteroid redirection test. And for the public, the most important point to make about the name DART is, next please, that it is a test. There is no known asteroid that poses an actual impact risk to Earth. The current impact hazard comes entirely from asteroids that we have not yet discovered, and the test is being conducted now when we don't need to do it in order to develop a deflection capability for the future in case one is ever needed for a newly discovered object. Next, please. So unfortunately, I can't show you animations in this presentation. If I could, I would be able to show you the orbit, the trajectory of the DART spacecraft. It's about a 10-month cruise from a launch window that opens up this coming November to a kinetic impact date in the Didymos system in late September or early October next year. The DART mission is targeting the binary asteroid Didymos and will impact on the secondary, the small moonlet of the larger Didymos asteroid called Dimorphos, and measure the period change from Earth. And it's that aspect, targeting of a binary asteroid and being able to measure the effect of the impact by measuring the change of the binary orbit from Earth, that is the key to the DART mission. Next, please. Just taking a slightly different perspective on this same diagram showing the DART spacecraft and the deployed LiCiA closely following, impacting on Dimorphos. This just makes the point that this binary asteroid is the ideal target for the mission and, in fact, a perfect natural laboratory for the experiment that we're going to do on the asteroid. Because part of the mission, of course, is to change the motion of the asteroid in space. And in this diagram, the way it's represented, the way it will most likely occur is that the spacecraft will hit Dimorphos head on instantaneously lowering the velocity and allowing Dimorphos to drop into a lower, more tightly bound orbit with a shorter orbital period. Next slide, please. So the reason this is the perfect target is that a binary asteroid allows a detectable deflection of an asteroid of relevant size, Dimorphos being a size typical of the most abundant objects that could cause serious damage. So DART's kinetic impact will change the orbital period of the binary by about 1%, which is detectable in a few weeks to months. If we were doing the same experiment with the same kinetic impact on a similar sized asteroid that was not in a binary, the effect on the orbital period around the sun would be 5 orders of magnitude smaller, which would take many, many years to detect. Next, please. So I'll briefly step through the level 1 requirements of DART, which Andy Cheng will revisit later on in this session. There are 4 requirements. First, to impact Dimorphos and demonstrate we can execute the kinetic impact. To change the binary orbital period. To measure the period change using ground-based observations, which Andy Rivkin will talk about later in the session. And also the 4th requirement is to measure beta, which was mentioned before in the HERA session. Beta is the momentum enhancement, the extra momentum imparted to the asteroid by the kinetic impact caused by the ejecta from the impact that are blown back along the trajectory of the impactor. Next, please. Now there's an important division which happens between requirement 1 and requirement 2. Of course, before the impact, there are DART spacecraft operations. Following the impact, there are no DART spacecraft operations because there is no DART spacecraft left to operate. And the interesting thing about the DART mission is that at that moment of impact, when the spacecraft no longer operates, a large part of the mission still has yet to be executed and a large number of the requirements still have yet to be met. Next, please.
Hey, Tom, about a minute and a half.
Okay, so DART is the double asteroid redirection test. Next, please. Not just because we're going to a double asteroid, but because it's also a double test. We're testing the ability to achieve a kinetic impact on a real asteroid, and we're testing how a real asteroid responds to the kinetic impact. The transition from that first test to the second test happens at the moment of impact. Next, please. So the spacecraft Lena Adams will talk about briefly. We'll talk about in a few minutes. I will only say that it's a simple spacecraft with a single imager, Draco, and the imagers on the LiCiCube CubeSat. Next, please. In the final days before, or final weeks before the impact is going to be tremendously exciting. We don't detect the Didymos system until about 30 days out. At 4 hours out, the autonomous navigation system is engaged. Next, please. And it's not until the final 60 minutes before the kinetic impact that the spacecraft is even able to see its target, Dimorphos. The automated system, the autonomous system, executes control maneuvers to make sure that we are heading toward the target. And in the last 2 minutes, the asteroid in the field of view of the instrument grows from a few pixels across to fill the field as image data is being streamed back at the rate of 1 per second. And then we obtain the last image of Dimorphos somewhere between 7 and 10 seconds out. We have loss of signal that confirms we executed the kinetic impact. That will be very exciting. Next, please. That will not be the end of the mission because, of course, the LiCiCube CubeSat will be following. I will skip over this because Elizabeth Dato will describe LiCiCube's observations, which will show us the ejecta plume and crater formation. Next, please. And finally, because I'm a theoretical astrophysicist at heart, I can't resist showing an equation because we do want that momentum enhancement factor beta. And you can write the whole thing down. And next, please. And the beauty of this equation is that the right-hand side contains all of the data products, all of the parameters of the mission. In green, the change in velocity comes directly from the measured period change. In yellow is the mass of the spacecraft and the direction of the object in orbit, which we know because of the encounter and the design of the spacecraft, of course. In blue, the mass of the asteroid, the direction of the surface normal vector, and the velocity relative to that normal are all constrained by DART and LiCi imaging of Dimorphos, and especially at the impact site. And finally, epsilon, the direction of the ejecta momentum vector is constrained by impact simulations and LICHA imaging. Finally, last slide to conclude. DART is 7 months from launch, 17 months from its kinetic impact on Dimorphos. DART will be a historic first test, both of humanity's ability to deflect a real asteroid and of a real asteroid's response to a deflection. And DART will enlarge our understanding of NEOs for planetary defense and planetary science, both on its own with LichioCube and synergistically with HERA. Thanks, everyone.
Great. Thanks, Dr. Statler. Next up, we have Dr. Elena Adams, the DART Mission Systems Engineer from Johns Hopkins University Applied Physics Laboratory. Dr. Adams will be presenting on the DART mission status for the next 10 minutes. Andy will give you a 2-minute warning. The floor is now yours.
All right, thank you. Can you guys hear me? All right, sounds good. Well, my name is Elena Adams. I'm the Mission System Engineer for the DART mission. Next, please. You just saw this graphic from Tom. We are launching later on this year, as he emphasized, just in 7 months, and we will be impacting Dimorphos in the late September, early October. So what I will talk to you guys about is really the overall status of the mission, where we are, how did we get here in the last couple of years, and where are we going. So if you go to the next slide. The big change for us over the last, I would say over the last year has been really that DART has been moved to our secondary launch opportunity. Originally, we were planning to launch in August of this year. However, we were directed by NASA to move to our new launch readiness date of 18th of November. And this new opportunity really allows us to meet the launching objectives just the same way. We just have a shorter time in cruise. We're still impacting Dimorphos right at the same spot. You can see right here, if we launch in the beginning of our launch period, we basically just make one rev around the Earth and impact on the 25th of September. If you go to the next slide, it changes a little bit. If we launch in 15th of February, which is the end of our opportunity, we impact on October 22nd. So one thing you notice that for a planetary mission, we have a surprisingly large launch period. So it's about 90 opportunities that we have. And the rest of the mission really doesn't change very much. We have some advantages to launching this late, such as we have a better ground coverage at launch and have a shorter cruise portion. So we really need to get things right on the ground the first time. And we still arrive just at the right time to both be close to Earth and have good radar and telescope coverage of our impact and post-impact. If we go to the next slide, the one small change compared to how we were hitting the asteroid prior to this is that for the first few days in our opportunity, we actually shift our orbit in such a way that it is shifted by about 20 minutes. So we don't impact where Dimorphos is farthest away from Didymos. We impact a little bit shifted. And that's really just the geometry works out that way. And our autonomous navigation can handle that. Okay, if we go to the next slide. So DART, of course, it is first and foremost a planetary defense kinetic demonstrator. And we accomplish it by using quite a few new technologies. So our most important technology is the smart navigation system. Tom talked about how it lasts 4 hours, the spacecraft is completely autonomous. And that's really made possible by the autonomous navigation smart nav system. It uses a Draco telescope, which is our only instrument, as the eyes to feed in images into the system, process them in the spacecraft on the CoreSat avionics, another one of our new technologies. It's an FPGA-based processor. Process all of the images and then tells the spacecraft to fire thrusters and maneuver us in such a way that we see and hit the asteroid. So, of course, there's LiCHA CubeSat, and Elizabeth is going to talk about it right after me. We are also demonstrating for NASA the NEXT ion propulsion engine, which is a new technology that NASA has been developing for over 16 to 17 years at this point, and it's all ready to go. We have a special antenna that's basically two pieces of aluminum, so some foam in between, called radial line slot array, and that's what allows us to actually stream images back to the ground, basically video, right before we hit Dimorphos. We are also demonstrating the rollout solar arrays, the first powered flight of those, which means they're really compact solar arrays that are rolled up, and they're very, very good for future missions to the outer solar system where the mass is a big deal. As well as we're carrying some constant radios on the solar arrays that would allow us to have 5 times as much power if needed. So these solar arrays are really there to make sure that they provide enough power for the NEXT propulsion engine. Go to the next slide. So in the last year, really has been all of us integrating and testing the spacecraft, getting ready for launch. What you see is a bunch of happy engineers on this image and working on the DART spacecraft. It's always important to show happy engineers. But we're also working with SpaceX because that's our launch vehicle that's actually going to take us into space. Next, please. So just a little bit of status of where we are. So the spacecraft integration and test is proceeding even in the COVID-19 environment. If you go to the next slide, in March last year, we had our integration readiness review where we basically said, okay, all of our electronics boxes and the spacecraft structure is ready, so let's go ahead and start integrating. And of course, COVID hit right at the same time. And a lot of the nations and a lot of the workforce went home. However, we did not stop. And it's very hard to integrate the spacecraft from home. So most of the time we actually are in the facility working with all of the social distancing, all of the COVID precautions, but we have been working the full year and actually have put together a whole spacecraft. You can see that our friends at Glenn Research Center and Aerojet brought us the NEXT thruster that has been completed. We all then integrated panels, got the spacecraft core from Aerojet, which was in Seattle, one of the early COVID hotspots. Our core set avionics together with SmartNav have arrived in June. And then if we go to the next slide, then solar arrays also did not stop. Our vendor in California did a great job working through COVID and getting us solar arrays. So here they're showing you how the solar arrays are being tested for the deployment. We tested the spacecraft in a variety of ways after we put it together, had a variety of mission simulations, including terminal rehearsals where we actually are hitting an asteroid. And after that, integrated the various components onto the spacecraft and had our pre-environmental review. If we go to the next slide. So at which point we realized that we are still missing 2 components. So our pre-environmental review, we decided that we are going to move to the secondary launch opportunity. And that's really because we were, with COVID, there were lots of delays and we did not have our solar arrays, nor did we have a Draco instrument. So the Draco instrument was being integrated at the same time and being put together at the lab. However, the spare telescope had a mirror failure where basically the primary mirror is separated from the rest of the telescope structure. And we decided after, a long review board, we decided that it is best that we modify the design of the flight telescope as well. And so we are in the process of actually rebuilding the flight telescope. At this point, it's expecting to arrive to the DART spacecraft in June. The rollout solar arrays, as I said, they were in California, they were being tested. However, California did have a lot of COVID issues, and so they did experience some delays due to that. And also they were just a new development. Sometimes the new development does take its time. So, but we have received the solar arrays and we actually are in the process right now, as we speak, of integrating them onto the spacecraft.
About a minute and a half, Lena.
Great. If we go to next slide. And actually right behind me, you can see the DART spacecraft being tested in the AMI chamber. So we started on our environmental review. We spent a month and a half in thermal vacuum, completed that recently. As I said, our solar arrays arrived. So at this point, we're testing the spacecraft, but we're really waiting for the Draco telescope to arrive. And after that, we will shake the spacecraft and simulate launch and the separation from the launch vehicle. And then ship to the Air Force base where we're going to be launching from in California. And then in November of 2021, we are planning to launch. So we're very excited. We've been working very hard to make sure that everybody is ready to both operate the spacecraft once we're in flight, but also ready to launch. So there you go. There's DART. Thank you. Last slide. Yep. Thank you, guys.
Great, thanks, Dr. Adams. Next, giving us a 5-minute overview of LICIACube will be Dr. Elisabetta Dotto from the INF Observatory of Rome. She's the science team lead of LICIACube. Andy will give you about a 1-minute warning before your time is up.
Thank you very much. So first of all, many thanks for the satellite of the binary asteroid Didymos. Next slide, please. Slide. Next slide, I don't see the new slide. Can you hear me?
Yes.
Dear Elisabetta, we can.
Someone can you hear me?
Your connection seems to be bad, so maybe you can turn off your video.
Yes, okay. So please, the second one slide before. No? Number 2. No? The slide before? The slide before, please. Okay, thank you very much. LICIACube is managed by the Italian Space Agency, and its team gathered together national research centers, academies, and private sector acting in Italy in the space domain. Next slide, please. This is a LICIACube, a CubeSat 6U of about 14 kilograms of mass. It's equipped with 2 different payloads named Leia and Luke. Leia is a catadioptric camera composed of 2 reflective elements and 3 reflective elements, and Luke is a camera with an RGB bioimpeller filter designed to work in focus between 400 meters and infinity. Here we have the characteristics of both the payloads, the focal length, field of view, integrated field of view, and the spatial scale reached at the LICIACube minimum distance from Dimorphos, which is of about 55 kilometers. Next slide, please. This is the nominal mission. LICIACube will be hosted by DART as a piggyback during the interplanetary cruise, then released 10 days before the impact on its autonomous path toward the target. And after commissioning phases and braking and correction maneuvers, LICIACube will approach the target and will perform the scientific phase during the Dimorphos flyby. After the Dimorphos flyby, LICIACube will downlink the obtained images directly to Earth. Next, please. Here we have the acquisition strategy, which is composed by 5 different phases. The first one for testifying the Dart impact, and here Luke will be not operative. Then we have the ejecta observation phase, the high resolution phase devoted to the study of the surface, the no impact hemisphere observation, the phase of observation of the plume evolution and forward scattering, and in all of these four last phases, Lenny and Luke will work simultaneously. Next, please. And here we have a summary of the scientific objectives of LiChaCube, which are testify and characterize the impact, obtain multiple images of the ejecta plume, and this will allow us to have measurements of the motion of the slow ejecta and estimation of the density structure of the plume. To properly interpret this data, we are developing models of the dust dynamics of the plume evolution. One of these models uses parameters that are constrained by the impact data or modeling, such as ISAIL or SPH codes, take into account the physical properties of the material which composes the target, and take it also into account analytical models of ejecta from asteroid physical properties. We are also developing another testing model on in-house simulated ejecta clouds to perform realistic simulations of the ejecta evolution of different time scales. Then LiChaCube will obtain multiple images of the Dart impact site to see the crater and have measurements of its size and morphology. And finally, we'll obtain images of the no impact hemisphere of the Dimorphos in order to increase the accuracy of the shape and volume determination and to constrain the surface alteration produced by the impact. High resolution images obtained at the closest approach will allow to study the surface morphology and the presence of boulders, large blocks on the surface of our target. In fact, by comparing pre and post impact surface areas, we can witness how the boulders size, frequency distribution and density changed as a result of the Dart impact. The loop data will give us also the opportunity to investigate the composition of the Dimorphos throughout spectrophotometric analysis. So we will be able to map the surface composition of the object and to derive the surface heterogeneity at the observer scale and to investigate the effects on the asteroid surface materials produced by the shock and those due, as an example, to space weathering. During the flyby, we also perform a radio science experiment exploiting the information carried by radio link between the spacecraft and the Earth, focused on the precise orbit determination and providing an assessment of the accuracies achievable in the estimation of the scientific parameters of interest, like as an example, the masses and the extended gravity field of the Didymos. Next, please.
About 30 seconds left.
Thank you. As above mentioned, the LiChaCube will downlink the acquired images directly to Earth after the Dimorphos flyby. We will benefit from the Space Science Data Center infrastructure at the Italian Space Agency for what regards the data management, organization, and exploitation. And we will also take profit from Matisse, an advanced tool that's developed at the Italian Space Agency. Next, please. This is the status of the project. Qualification test campaign at CubeSat level is presently ongoing. Here we have the schedule for the next steps, and the delivery is expected on 33rd July. And next, please. This is my last slide. Thank you very much for your attention.
Great. Thank you so much, Dr. Dotto. Next up is going to be Dr. Andy Rifkin, one of the DART investigation team leads from Johns Hopkins University Applied Physics Laboratory. He's going to be giving a 10-minute presentation on how we will know what we've done, observations and dynamics. And Andy, I will give you the 2-minute warning.
All right, sounds good. So hello, everybody. It's a pleasure to be here. Thanks to us for inviting us, I guess. So next slide, please. I'm just going to flash through some things here. Here again are the level 1 requirements that Tom mentioned. I'm just going to mostly talk about number 3 here, measuring the period change, and then just a little bit about the dynamics that we're trying to characterize. Next slide. So what we currently know about Didymos is actually more than nothing. It's not as much as we're going to know. But what we know basically comes from 3 different kinds of data sets. We have light curves. I'm going to talk more about those on the next slide, where basically we repeatedly image Didymos as it moves across the sky, measure the brightness variations for those of you who are not astronomers. We have a radar shape model, which was obtained in 2003 when Didymos made a close approach to Earth. And a combination of the light curves and the radar data is what told us that Dimorphos existed. There are also some reflectance spectra that have been obtained over the years that give us a handle on the composition. We think it's very similar to the L or LL meteorites, LL or LL chondrites, which are the most common type of meteorite falls found here on Earth. Next slide. So like I said, light curves are really important. Light curves have been the most important data set where we've gotten most of our information thus far about Didymos. Light curves are going to play the key role in the post-DART arrival data set. And basically what we do with these schematically here on the bottom, this is a frame from an animation. The brightness of the system goes up and down with these dips occurring when Dimorphos moves in front of Didymos and blocks some of its light and casts a shadow on it, or moves behind Didymos and is itself blocked. And the frequency or the time between these so-called mutual events gives us the timing on information about Dimorphos's orbit, and then the depth of the cutouts there tell us about the relative sizes of the bodies. So to say it most simply, we measure the change in the light curve before and after to tell us how we have changed the orbit of Dimorphos. So what we know about, next slide please, what we know about the system so far, again, in terms of its scale, it's a very human scale system. Dimorphos itself is kind of similar in size to the Great Pyramid of Giza. It's a bit taller, but it's not as broad as the base of the pyramid there. Didymos, the main body, is kind of similar in height to the highest skyscrapers we have on Earth. DART itself is down there on the left. It's 19 meters if you include the solar panels. The main body of it is, we decided earlier today, about the size of a vending machine or maybe an upright piano. Next slide puts this again on a scale that some of you might be familiar with. Here's the system compared with kind of the inner part of Vienna, where hopefully we'll next be meeting in person. And again, it's a very walkable system. If you were to be able to walk it, people, you know, that puts it on a scale, you know, where it's the size of kind of a typical downtown area or even smaller. Next slide. So the observations that we've done this past year and that are coming up, I'm going to summarize here. On the right, there's a plot that shows kind of the current Olympiad from January 2020 to January 2024. The top slide shows the V magnitude, the brightness of the system. The bottom one shows the solar elongation. The shaded regions on the top panel show the times when it's more than 90 degrees from the sun in elongation, and then the solid vertical line shows the date of impact. So earlier this year, there was a lot of observations of Didymos that were focused on trying to improve the precision of the orbit to allow us to arrive with DART at the time we wanted to and at the orbit phase we wanted to. These observations took place December through March. Early observations only had a very short observing window, and then we had kind of a deadline-driven data analysis that included observations from LDT at Lowell and the Keck observatories. Next slide shows the results. And here are some of these light curves I was talking about. The first and third panels show the overall light curve that you get from all of the data. The second and fourth have the rotation of Didymos taken out and show these dips that are due to these mutual events. So we've been able to reduce the uncertainty through these observations. So we know Dimorphos's orbit period to about a 100th of a second. The 3 sigma uncertainty on Dimorphos's orbit phase is less than 7 degrees when we extrapolate it to the time of DART arrival. So we know we can hit it head on, or as close to head on as we want, as Lena had pointed out. The GM value hasn't actually changed. We've known that pretty well. It corresponds to a mass of about 5.5 times 10 to the 11 kilograms. Most of that mass is in Didymos, and the best fit density is about 2,170 kilograms per cubic meter. The next slide here, this just shows we have these numbers, we put them in a table, that's what that is. The next slide is a plug for a couple of lightning talks by Christina Thomas and Shantanu Naidu, which go into a lot more detail about the observations and about how these orbital parameters were determined. Next slide, please. So this talks about then the observations we are still to do in the future, this right shaded region. So Didymos spends a very long time, over a year, at greater than 90 degrees solar elongation, and roughly 6 months at visible magnitude of less than 17.5. That's the 2 vertical lines that are dashed that flank that solid vertical line. And at that period, when it's 17.5 magnitude or brighter, we should be able to get good light curve data with sort of meter-class telescopes. So the DART project is supporting observations from 4 observatories in the northern and southern hemisphere. Lowell Observatory in Arizona, the Magdalena Ridge Observatory in New Mexico, Las Cumbres Observatory Network, and then Las Campanas Observatory in Chile. The team members have access to additional observatories around the world, which will also give us more opportunity to observe. At the time that DART arrives, it's going to be in southern skies, but it moves north rapidly over the following weeks. So the next slide shows that. This is a kind of an old school star map from back in the day, but the points there show Didymos's position every 5 days. It starts kind of along the right edge in September 2022. We've circled the date that DART arrives, or the date closest to DART's arrival. It's in the southern sky, and again, it moves rapidly north and kind of hangs out for a while in northern skies. Next slide. This shows the coverage that we expect to have from various observing sites. The top slide shows, that's the top panel, shows the best air mass reach. That's basically the elevation above the horizon, and how with time it changes from being best seen in the south at Las Campanas and other observatories at longitude in Australia and South Africa. And by the end of October and early November, it's well placed in places like Hawaii and the southeastern United States and other places at those latitudes. And the bottom slide bottom panel is just another way of showing that with hours above 30-degree elevation. The next slide. Just
Andy, you have about a minute.
Okay, I can do that. The next slide talks about some additional measurements. We will have some radar measurements from Goldstone, possibly bistatic with Greenbank. I don't know how those plans are going to play out. We are hoping to measure ejecta not just from LICHA-Q, but potentially from the ground. We expect the system to brighten while the ejecta is still unresolved within the same pixel as Didymos. So we are hoping to be able to study the ejecta evolution as possible. Next slide is a plug for some e-posters and e-lightning talks that also talk about these plans. And then the home stretch here, next slide, the dynamical possibilities. Inevitably, we're going to cause librations when we impact Dimorphos, because if you take a perfectly circular orbit and you do anything to it, you make a non-circular orbit, and that means librations. The amount of libration is going to depend on Dimorphos's shape. It's not clear if we'll be able to observe it from Earth or not, but we do hope that if we do something, that HERA will be able to observe it, just again showing how the combined data sets will be more than the sum of the parts. And the specific dynamics of what happens is going to be sensitive to initial conditions, the shape of Didymos and Dimorphos, and potentially their internal structures. The next slide is my last plug here for, again, some e-lightning talks that discuss the dynamics. So my last slide here is just a summary, and I see Dawn has appeared, which means my time is up. But basically, telescopic observations are integral to the whole project. Dynamical studies have also been important. And preparations for the 2022-2023 observations are beginning, and with the opportunity for folks to participate. Thank you.
Great. Thanks, Dr. Rivkin. Finally, we have Dr. Andy Chang, another one of our DART investigation team leads from the Applied Physics Laboratory. Dr. Chang will now speak to us about the DART legacy for the next 10 minutes, and Andy will give you a 2-minute warning.
Thank you. So let me talk a little bit about, mostly about determination of beta and about the information that DART will return and its value for planetary defense. So next slide. All right, we've already heard about DART as the demonstration of a kinetic impactor at Didymos to impact the moon Dimorphos, to change the binary orbit period, as we've heard, also to measure the period change with ground-based telescopes. And what we need to do also is to measure and characterize and understand the momentum transfer, beta, the momentum enhancement factor, which we've heard a little bit about already from Tom. Next slide, let me talk about it in a little more detail. Okay, so look on the left. It's conventional to talk about the momentum transfer efficiency in the following terms. You draw a one-dimensional picture. You have an incident kinetic impactor, brings in momentum, it hits a target, and it causes a momentum transfer. And all of these vectors, the incident momentum, the momentum transfer, are thought to be just written as collinear vectors. So it's a one-dimensional picture. And in that case, the beta is simply the ratio of the enhanced momentum, the final momentum transfer to the initial momentum. And beta can also be written as 1 plus the ejecta momentum divided by the incident momentum. And so the sketch there shows what's happening. Why is there an enhanced momentum transfer? It's because you create impact ejecta. They fly off, they carry off momentum. They are in the backward direction. And so your impact site, or your ejector crater, if you like, it's acting like a little rocket. It's throwing material back and thereby producing a thrust in the forward direction. Okay, now the problem, this is all fine in principle. The issue, of course, is that for an actual experiment, DART is an actual experiment in this deflection, we have to take into account the three-dimensional geometry. And the reason is that these vectors are, for the DART experiment, not going to be collinear. And so what you write instead is the momentum balance, that's the top equation on the right, which says that the momentum, the final momentum of the body, capital M is the mass of the target body, something we need to know. Little m is the mass of the projectile. And you have two terms. You have the incident momentum and you have the momentum carried away by the ejecta. So those are the fundamental properties, the fundamental entities that play in this game. And the magnitude of the ejecta momentum is represented by this factor beta, and this little, and the direction that the net momentum carried away by the ejecta is in the vector, the unit vector n. So my notation is a little bit different from Tom's, but I'm trying to make this a little bit simpler. So you have an ejecta momentum that's in the direction n. If you have a smooth surface, if you have a DART impact that is not too oblique to that surface, then the ejecta momentum n is also the outward normal vector of the surface. But if they have, it's very likely if you have a very bouldery surface, if you have topography, small scale topography, if you have features, in other words, on a scale of meters, on the order of meters, then the ejecta momentum is not necessarily going to be the outward normal. And in fact, it's even a question of exactly how would one define outward normal if in fact you have features on this, boulder size features on the surface. What is the normal vector at the impact site? Anyway, beta in this, from the first equation you see on the right, you can show easily that the beta is, in fact, as look at the sentence below, it's the transferred momentum component along this direction n. This is the net ejecta momentum direction. So beta is the transferred momentum component along that vector divided by the incident momentum component along that vector. So this is a general three-dimensional definition of beta. It's a scalar quantity. We choose not to characterize the momentum transfer with a tensor of any kind. Instead, the definition of beta in the general 3D involves two vectors. So it involves the incident direction and the ejecta momentum. The third vector which enters into the problem, of course, is related by the momentum balance. So there's really two independent vectors that come into this. Okay, next slide. So that's it. Okay, so how is DART going to actually work out beta? First thing we need to realize is that the fundamental DART measurement, which is the binary orbit period change, that effectively is a measurement of the transverse component. It's the component of the velocity change along the orbital motion. So it's one component of three. So we don't actually measure the vector velocity change of the target. We measure one component of it. We measure the dominant component of that velocity change, but not the other two components. We will not have another spacecraft rendezvous with Didymos watching the impact. That would have been true if we had the AIM spacecraft. We don't have that because the HERA spacecraft, as we heard, will arrive about 4 years after the DART impact. So the other two components of velocity change are not observed for this DART experiment. So what are we doing about that? Well, we're going to use full two-body numerical modeling of the binary, the Dimorphos-Didymos binary, to be able to relate the period change to the vector three-dimensional velocity change. So that's a matter of orbital dynamics, and our best bet to be able to relate those two to determine basically the other two components of the velocity change is indeed with the full two-body numerical modeling. As a note here, the reason why we have to do this is that, of course, Didymos and Dimorphos are not spherical bodies, and they're not well separated spherical bodies. So they're irregular bodies, and they're very close to each other. So there is a strong spin-orbit coupling in the system. The result of which is that the Dimorphos-Didymos binary system does not actually obey Kepler's third law. Okay, it's close. The Kepler's third law is accurate.
2 minutes left, Andy.
1% or so. Yes.
2 minutes
How
left.
much?
2, now less.
Okay. All right. So we are also going to be measuring. So also going to be measuring size, shape, and we have to determine the mass of the target. Okay, let's assume now that we have estimated the velocity change from the impact. We now have to get the mass to do the momentum transfer. And one approach is, of course, to measure size, shape, volume of Dimorphos. That's with imaging, both from DART and from LITCHA-Cube. So we'll see with LITCHA-Cube actually both sides of the target. And so infer mass that way. Okay, we also have the DART approach imaging. We want to characterize the impact site, where it hit, and also what is the geology and topography there, in part to understand the impact dynamics, and in part also to be able to estimate what the surface normal might be. What kind of surface did we hit, and what might the direction, what would we expect the direction of the impact ejecta to be? as we have heard from Elisabetta, also LichCube is directly observing, measuring, imaging the ejecta plume, and those images will also directly constrain the direction of the plume, and so the direction of the momentum transfer. And that we hope also will give us a good estimate of this vector n. And finally, impact simulations, detailed impact simulations to understand the effects of the spacecraft geometry. The spacecraft itself is also not a point mass or spherical uniform mass. A spacecraft has a shape and a mass distribution. Okay, we have to understand what that effect is, as well as the impact site topography, the fact that we're not going to be hitting exactly normal to the surface, but we have some angle. Okay, and finally, of course, an estimation of the uncertainty. What kind of range of impacts could be consistent with all of the observations that we're measuring? Okay, next slide.
Gotta wrap it up here, Andy.
Okay, the DART archive, data archive. So the main point I want to measure, of course, main point is that, yes, the DART image data sets, the LichCube image sets from both cameras, they will be archived in PDS, and as well as that, the ground-based data sets. So we are listing here the ground-based telescopes that will be their data sets, telescopic data, as well as the radio science data and ancillary data. Okay, so I think the last slide is coming next. Yes, I was going to talk about all right, okay, I'm finished, I gather. So.
Great. So thank you, Andy. So I just want to give a sort of virtual round of applause to all of our speakers for such a great session. We do have some questions in the chat, and I think we have about 5 minutes that we can do these. And so I'll start out with the first question that I see. So given the surprising 50 centimeter penetration below Bennu's surface during OSIRIS-REx, sorry, it just jumped, tag event, how does the difficulty of predicting the porosity of asteroids play into DART? How can the high porosity disrupt the deflection by the kinetic impactor? And I think I'd like to also extend this question, you know, what sort of influence would a high porosity have on, say, the observations that LichCube might make as well? And so I'll kind of open up to everybody, and anyone can feel to jump in and answer.
Let me just say a few things. I think Elisabetta may want to talk a little bit, but okay, a highly porous target, or which we in most cases is also going to mean a very weak target, because I think that's the implication of the very deep penetration for tag. It's both a very low strength target and a high porosity target. When you make that kind of a model, it turns out that yes, you have a lot of ejecta. So it creates a, you predict a large impact crater, which is similar to what was seen also with Hayabusa. So a large impact crater, possibly, depending on how large the crater is, it's possibly large enough that you begin to see the curvature as effects of the body. It's that large. So that's going to be very strange, very interesting. Large amount of ejecta means a dense ejecta plume. It means also a long time scale for evolution. But so the LichCube images will clearly be able to distinguish that. The impact, okay, the beta values turn out to be high, but not terribly high. So you're still getting betas in the 1.5 range. So Dawn, you can maybe talk to that as well. That's where impact simulations would indicate.
Can I add something to that? The question was about disrupting the deflection. I don't think porosity is going to disrupt the deflection at all. The asteroid is still going to be deflected. And furthermore, even if there is no momentum enhancement effect, even if beta is 1, this is still easily detectable from the ground. So the porosity is going to affect the details of what we get out of the experiment and what we learn about the asteroid. It's not going to disrupt the deflection test itself.
I will underscore and underline what what Tom said. I mean, momentum still has to be conserved in a perfectly, in the inelastic collision, DART would come in, and if it buried itself, in the center of Dimorphos, it would still be carrying whatever momentum it brought with it, and that would still move Dimorphos. The ejecta then carries whatever extra momentum in whatever direction. But and then I know people were saying they wanted Elizabeth's take on this also, but so I don't want to cut her off.
Elizabeth, is there anything you would like to add to this?
Yes, in our modeling, we are considering several examples and several cases. We are working with best case.
Whoops. I think we lost you, Elizabeth.
Still there, Elisabetta?
I think we lost her. We should
Yeah, I
go
think
on
we
to another
lost.
question or finish
Yep.
up.
So another question that was asked was, to accurately estimate beta, we need to know more or less the exact mass and velocity spectra of the ejecta. How do we get this spectra from observations, or what model will be used for that?
Well, actually, I can take the beginning of that. Actually, you don't, strictly speaking, because, of course, we know we're going to measure what the effect was from the change in the period. We know exactly how much momentum we're delivering. And so by comparing those two, you can figure out what is the excess percentage of momentum that was contributed by the ejecta. And so beta comes out directly without knowing exactly what came out of came off the asteroid in terms of ejecta. Now, there are two places where you have to modify that. One is that you do need the imaging or knowledge of the orientation of the surface to know what direction the ejecta came out. And also having the additional information both from the LiCheCube imaging, observing the ejecta plume from multiple directions at multiple times, and also against the space background and against the lit up body of the asteroid, will give us the ability to get constraints on combinations of the optical depth and the particle size and the time development. That will be additional constraints on the ejecta development. And especially, it's going to be tremendously exciting if the cratering really is in the gravity regime without any cohesion. The very, very low velocity ejecta will still be coming out of the crater at the time LiCheCube flies by, and that's going to be an additional constraint on the physical properties, which will then play into the simulations to let us better understand the surface properties of the material.
Great. So I actually think that this is all the time we have for this session, and before the next session begins. Again, I want to thank all of our speakers for giving us great talks. There are a couple more questions in the chat, so I would just sort of refer our speakers to maybe take a look at those and maybe answer them if they have time. And again, I just want to put an additional plug for all the e-lightning and poster sessions that might be relevant to the DART session. So thank you, everybody.
And my co-chair is Dr. Christian Kerbel, pardon me, who's a professor at the University of Vienna. As with the DART session, we will have a series of talks, and then we'll have a time for question, answer, and discussion at the end of the 4 talks, which will each be 10 minutes. The first talk is by Dr. Amy Simon, a senior scientist at NASA Goddard Space Flight Center, who'll be presenting overview and highlights of the OSIRIS-REx mission, and we'll give you about a 2-minute warning when you're coming up in your time. Take it away, Dr. Simon.
Okay, thank you very much. And good afternoon or good evening, depending on your time zone. So I'm going to start us off with a little bit of an overview of the OSIRIS-REx mission, some of the phases that we went through, and then some science highlights focusing in particular on the spectrometer results, because you'll be hearing more about some of the other results in the later talks. Next chart, please. As many of you, probably most of you know, OSIRIS-REx is primarily and first and foremost a sample return mission, but OSIRIS-REx is an acronym, and it basically is describing all of our main scientific goals with this mission. So origins, spectral interpretation, resource identification, security, regolith, explorer. So origins, again, bringing back our pristine sample, hopefully a sizable sample from asteroid Bennu. Spectral interpretation, so providing the ground truth for our telescopic data, so the connection from Earth-based data to remote sensing in orbit all the way down to our sample. Resource identification, mapping out the composition of the surface. Security, the Yarkovsky effect, which you'll also hear more about. And then regolith explorer, documenting down to the centimeter scale. Next chart. So OSIRIS-REx was selected in 2010 and it launched in 2016. After an Earth flyby in 2017, we arrived at the asteroid in late 2018. And this was the general timeline. Things have shifted around a little bit. But basically, as soon as we got there on approach, we started to take data to understand what the surface of this body was like, all leading up to this sample acquisition and then eventually Earth return. Next chart. This is the science phases at our asteroid operations plan. Again, these dates shifted a little bit, basically because we had time, but the idea was that we would start on approach before we even got into orbit, doing our navigation, making sure we understood the gravity environment and taking our initial science data. But the primary science phase was our equatorial stations detailed survey and baseball diamond phase, where we basically mapped out the entire surface with all the instruments. From that, we were able to do our sample site down select down to 4 possible sites, and then we did reconnaissance flyovers of those to pick the best one, all leading up to our rehearsal and our tag. So next chart. So what did we see? Well, on approach, we saw boulders and more boulders and lots of boulders. Everywhere we looked, there were boulders. Not a lot of clear, smooth areas, which we were hoping to see for our sampling. So as you can see right from the start, this presented a bit of a challenge for us, which was how do we map this out to really the centimeter scale to be able to find that clear sampling ellipse, which had to be much smaller than we originally intended. So as part of this, we did our full mapping of the surface. Next chart. And from that, we were able to look at composition. Now, overall, Bennu has a blue spectral slope. It's pretty blue wherever you look. There's a few spots that are slightly more red, but there's very little surface variation really at a big scale. We do see evidence of hydrated phyllosilicates all over the surface. Again, very small differences in absorption depth, but it is all over the surface. Carbon-bearing materials, we see a 3.4 micron absorption band, could be carbonates, can be organics. Again, very small variations on the surface, at least at that large macro scale. And we do see some evidence of iron oxides as well. In addition to this, we have a couple of very bright boulders on the surface. These appear to be exogenous material, pyroxenes, very similar to the Vesta meteorites. Now, if you zoom in at the finer scale and look at these rocks up close and these boulders, you will actually see some variation in them, including what appear to be bright veins, probably a carbonate. So we do see quite a bit of heterogeneity at that very fine scale. Next chart. We also looked at thermal inertia, and we expected to see these very large boulders to have high thermal inertia and our dusty areas to have low thermal inertia. And we kind of found the opposite of what we expected, where the equator was very high thermal inertia and our boulders were low. So this could be possibly due to compaction around the equator or the boulders being very porous. So this is all fed into our analysis as we looked at safety. And our sample site, which I can't point out, but it's around 60 north and 45 east, is slightly lower thermal inertia than the rest of the surface. Okay, next chart. So then we had our tag event. And if you look at the sample head and look at the rocks immediately around it and go to the next chart, you'll see as we touch that they move or they appear to crumble. So there was quite a bit of activity just touching the surface of Bennu. And then next chart. And then we fired our nitrogen gas. And then you see these rocks and cloud of dust kind of go in all directions. So You know, in the end, we picked a very good sample site. There was a lot of loose material. It did not take much to move it, so that was a really good sign for us. And even before we got any visible measurements of the sample head, that there was probably a good loose sample in that region. And of course, I'm sure a lot of you have seen the images taken since we've gone back for a final look. So next chart. Just a little timeline of what happened. We were moving down to the surface about 10 centimeters per second. We made contact. The head kept sinking at that point. There was nothing to really slow it down. As you saw, that surface really kind of crushed in. Then our gas piles fired, so nitrogen gas for about 5 seconds, and that's the cloud of dust that you saw. At this point, OSIRIS-REx was still sinking until we fired our thrusters, and then we backed off at 40 centimeters per second. So this is going to tell you a lot about that surface and the stiffness and how hard it is. We never hit hard rock that really stopped us, which is really quite interesting. So we'll be looking forward to our sample coming back in September when we can really look at what we got off the surface and what that tells us in terms of, in particular, planetary defense, how these rubble piles are held together. Next chart. So in summary, Bennu had a lot of surprises for us. We didn't have big ponds of regolith. We had lots of loose rubble, lots of boulders all over the place, but we appear to have gotten a very sizable sample from that. The composition and spectral slope are fairly uniform across the surface, at least at the large scale, the 20 and 30 meter scale. About 90% of the surface is blue with a few red boulders and craters, and really only small variations in absorption band depths or band identification, with the exception of those few pyroxene boulders that we do see on the surface. We do see ample evidence of past aqueous alteration. The fact that we have hydrated phyllosilicates, we potentially have veins of carbonates, and we do see iron oxides. And so now we've just finished our farewell views of Bennu this past month, and we depart in May in just over a couple weeks, and our Earth return is in September 2023. So hopefully everybody stays tuned for that. And I will stop there.
Thank you so much for that overview of OSIRIS-REx. Our next talk is from Dr. Ron Balouz, who's a postdoctoral researcher at the University of Arizona, and he'll be giving a talk constraining the strength of 100-meter scale asteroids through craters on Bennu's boulder and NEO population estimates. Take it away, Dr. Balouz.
Thank you, Tarek. Hi there. So today I'll talk about the craters on Bennu's boulders, how they provide an estimate of the strength of 100-meter asteroids, and how the NEO population estimates may allow us to validate some scaling relationships that we came up with. Next slide, please. This is an outline of the presentation. I'll first talk about the observations, then I'll give an overview of the strength model and results. Then in the context of these results, I'll show how NEO population dynamics can provide an additional constraint. Finally, I'll link our findings to some open questions in planetary defense. Next slide. We first discovered craters on Bennu's boulders in images taken during the orbital phase of the OSIRIS mission. In total, we measured more than 600 craters on boulders, and these craters range in diameter between 3 centimeters and 5 meters. On the right, I show 2 images of boulders with craters, as well as their corresponding 3D point cloud data, returned by the OSIRIS-REx laser altimeter, or OLA. The color in the OLA data shows the height relative to the best fit plane to the crater rim. Next slide. Here I show more detailed measurements of crater on boulder morphologies. The images on the top panel show the position of the craters relative to their host boulders, and the yellow dashed line in those images correspond to the topographic profiles of the craters that we show in the bottom panels. You can see the clear impact crater morphology. Some craters are large relative to their host boulders, and for these we found a depth to diameter ratio of approximately 0.33, which is high compared to that of large craters measured on the Bennu surface by Daly et al. Next slide. So the question is how we obtain information on boulder strength from observations of their craters. The answer we found is that there should be a theoretical maximum crater size that a given boulder can express on its surface before it's catastrophically disrupted. We parameterize this as the ratio of crater size to target size, or RC over RT for short. For a given material type, there should be a maximum RC over RT. At equilibrium, we can relate the mechanics of impact cratering to catastrophic disruption. Next slide. To summarize, the crater measurement allows us to construct an empirical catastrophic disruption curve for C-type objects. The catastrophic disruption curve defines the energy per unit mass required to reduce the mass of a system by half. As an example, main belt disruptions would be described by the shaded curve shown here. And the catastrophic disruption curve is composed of two main regions. At small sizes, a regime where the material strength of an object dictates its resistance to disruption. At larger sizes, gravity dominates instead. The measurements we reported here allowed us to directly obtain the size scale dependence in the strength regime. We are also able to get an estimate of the impact strength. From this, we find that a meter-sized boulder on Bennu has a compressive strength of about 1 millipascal and a catastrophic disruption threshold between 200 to 300 joules per kilogram for a 5 kilometer per second impact. This is similar to strength obtained for Ryugu's boulders from Mascot and is in the lower range for meteoritic analogs to Bennu. Our interest here is to use our scaling relationships to obtain the strength properties of 100-meter scale asteroids, which lie in the transition regions between strength and gravity scaling, where object can be considered to be weakest, which is the minimum in these curves. Next slide, please. Let's now consider the size frequency distribution, or SFD, of asteroids. The black data and model show the main belt SFD, which is the reservoir for NEAs. The blue model shows the NEO SFD, and the red data shows the NEOs that have actually been observed up to June of last year. With the spacecraft, we visited objects that sampled different parts of these distributions, from Vesta and Mathilde on the large end to NEA's Eros, then the rubble pile Bennu, of course. As you'll notice, the transition to rubble piles also coincides with an inflection point, the NEO SFD. So an open question here is, what objects smaller than 200 meters actually look like? Are they rubble piles or monoliths? Understanding the physical characteristics of this size class is important for planetary defense because they are the most numerous objects that would also have a subglobal effect if they impact Earth. Next slide. First, let's consider the case for a rubble pile structure for these 140-meter asteroids. One of the main observations that allowed us to infer a rubble pile nature of kilometer-sized things is the distribution of their spin periods, which we show on the right. The majority of asteroids larger than 200 meters do not spin below 2 hours, which is the limit for a cohesionless object. However, through numerical simulations, we know that a rubble pile with some cohesive attraction between its constituent particles can exist past the spin barrier. So it may be that the fast spinners are rubble piles with modest levels of cohesion, about 3 kilopascal at most. However, the tensile stresses of even the fastest spinners are well below the tensile strengths inferred from meteorites and bolides. This may be because of hard limits in exposure time required to adequately sample the rotation periods of ultra-fast spinners. Next slide. Now let's consider the case for monoliths by using that inflection point I pointed out in the NEO SFD. O'Brien and Greenberg showed that the collisional equilibrium of two distinct subpopulations, one dominated by strength and the other by gravity, will generate waves in the SFD of the entire population. This creates an inflection point where the subpopulations intersect. The intersection point could be where the populations transitions from rubble piles to monoliths. And the amplitude of that inflection point, which we show here as this delta log n function, is directly related to the number of 140-meter objects. Furthermore, the amplitude can be estimated if we know the impact speed and the strength properties of the collisional population. So we have directly determined some of these strength properties from our crater measurements. Others are tightly constrained, and some we have assumed from experimental measurements of analog objects. Next slide. Putting those all together, we can compare our strength measurements directly with current estimates of the NEO population. So this plot shows the amplitude of the inflection point on the left and the cumulative number of 140-meter objects on the right vertical axis. They're equivalent. The black curves show population estimates for different strength properties. And then the blue shaded region is our strength estimate based on crater on boulder observations. And the red line is the current population estimate from Harrison to Bramo, which is within the error range of our strength measurements. Next slide. So if that population estimate holds, then we would be able to infer a few things. One, that there is indeed a transition from rubble piles to monoliths in this size range. Two, that these monoliths will have similar properties to large boulders on asteroids, like the 160-meter boulder Otohime on Ryugu. And third, the strength properties estimated from boulders will reflect the properties of the 100-meter scale population. So based on our scaling relationships, these would have a tensile strength of about 0.13 megapascal and a disruption threshold of about 30 joules per kilogram for a 5 kilometer per second impact. Next slide. Next slide, please. So to summarize, thanks. To summarize, we use these measurements of craters on boulders to develop strength scaling relationships for solid asteroids. Then the collisional equilibrium that creates the NEO population can also place some constraints on their strength properties. The current population estimates of objects greater than 140 meters are consistent with our strength estimates, suggesting that this population may be dominated by monoliths, and we've been able to calculate their impact strengths. These conclusions can serve as hypotheses that will be tested with next generation NEO surveys and the return samples. Looking forward, we now know that the impacts on the surface of rubble piles can have very different outcomes. If the SEI impactor, for example, would have made a much smaller crater if it had impacted a large boulder on Bennu. Furthermore, Dimorphos as a secondary is likely a rubble pile based on our current understanding of binary NEA formation. So it may be that the sub 200 meter population is heterogeneous, composed of both rubble piles and monoliths. But it's clear that the various activities of the planetary defense community will address these open questions in the decade ahead. That's all I have, and thanks for your attention.
Thank you so much. And I didn't give you the warning because you were right on time. So the next presentation will be from Dr. Bo Bierhaus, who is Senior Staff Research Scientist at Lockheed Martin Space, and he'll be giving the talk Bennu Craters in the Context of Planetary Defense. Take it away.
Thank you, Derek. And I appreciate the invitation to speak at this year's Planetary Defense Conference. It turns out nature, runs impact deflection experiments all the time. This is in fact impact cratering itself. So we should maximize our understanding and our knowledge of cratering on rubble pile asteroids to inform kinetic deflection techniques. Next slide, please. Okay, this is the first of just a few slides to introduce you to the crater population that we measured on Bennu. This is a map of 1,560 craters across the surface of Bennu. And we measured diameters from less than a meter to over 200 meters in diameter. Next slide, please. These two images are the same crater database, but now plotted on top of a Bennu shape model. And the shape model has been colorized by facet radius, or basically just the distance of a surface element from the center of the body. And you can see that the craters do indeed span from the equatorial region all the way up to the polar region. And these measurements were enabled by the incredible data set that OSIRIS-REx collected during its operational phase that Amy described earlier. We have literally thousands of images and literally billions of LiDAR spots that were collected over the course of this mission. And the LiDAR data were accumulated into digital terrain models that allowed us to observe the craters and measure them at high latitudes, and especially in the polar regions. The LiDAR data were helpful there. And this illustrates the truly global nature of this data set. Next slide, please. One of the fundamental analyses that researchers like to do with crater populations is to examine their size frequency distribution, or SFD. And different researchers prefer different formats of the SFD, and so I've got the three primary ones plotted here. On the left is the cumulative size frequency distribution, and this is essentially just the diameter at a given size and larger, how many craters are at that size and larger, and it's normalized by the surface area. In the middle is the differential format, and this is essentially a histogram where now you're looking at the number of craters that are within a certain diameter range. And the plot on the right is the relative, and this normalizes the differential to a single power law exponent, and it allows you to examine the variability of the population against a single power law. And if it were a single power law, the relative plot would be a horizontal line, and the fact that the relative plot is not a horizontal line means that the population is not well described by a single power law function. But for the remainder of this talk, I'm going to focus on the differential format, which is the plot in the middle. Next slide, please. You'll see in the differential plot that somewhere between 2 and 3 meters diameter, there's a rapid fall off in the crater abundance. And with differential plots, this is actually not uncommon, but that fall off is typically associated with the finite resolution of the data you're using to make the measurements. And it's essentially as you're making measurements at smaller and smaller diameters, eventually you're measuring things that are only a few pixels across, and you're not going to be able to observe them, to the point where if something is only 2 or 3 pixels across, it's hard to know whether or not it's actually a crater. And so the differential format often has this rollover, and that rollover is associated with the finite resolution of the data set. And that rollover diameter is often called the completeness limit. The completeness limit is usually between 5 to 10 pixels diameter, depending upon the surface and the nature of the data set. And I've plotted the 10 pixel point, or the 10 pixel diameter on this plot. And you can see it's still a factor of several smaller than the diameter at which we observe the rollover. In fact, the rollover occurs at 40 pixels across. And so that's a factor of 4 to 8 times larger than the standard completeness limit. And we've done another number of other studies to demonstrate that, in fact, this is the real size frequency distribution. This is not a resolution effect. The impact crater population does increase with number until around 2 to 3 meters diameter, and then it falls off precipitously. So it's a real effect. It's what's happening with the crater population. Next slide, please. Okay, here I want to introduce a new topic, impact armoring. A series of recent experiments that were inspired by the first Hayabusa mission to the asteroid Itokawa revealed a previously underappreciated effect when the impactor diameter is comparable in size to the target boulder diameter on the surface. If you think of the moon does have boulders that are, a meter or even much larger, but the vast majority of the surface area of the moon is covered by dust, very fine-grained particles that are tens to hundreds of microns in size. And if a 10-centimeter impactor strikes those dust layers, that 10-centimeter impactor is much, much larger, and that impact surface can essentially be treated as a continuum. That's not true on the surface of rubble pile asteroids. And the purpose of these experiments, the goal of these experiments, was to understand what happens in this regime where the impactor is roughly the same size as the target boulders. So I pulled out a plot from this really fantastic paper by Tatsumi and Sugita in 2018. The horizontal axis of the plot is the ratio of the projectile diameter to the target diameter. And the vertical axis is the ratio of the impact energy to the disruption energy of the boulder. And that was something that Ron was talking about in his previous slide, or in his talk. And they found that there are two impact armoring regimes that occur in these kinds of impact scenarios. The first impact armoring regime, which is in the upper left-hand quadrant, you make a crater, but that crater is smaller in size than what you might expect by applying that impactor to, say, the moon. The second armoring regime is in the lower left-hand quadrant of this plot. And here, crater formation is actually suppressed. You don't actually make a crater. And we were wondering whether or not this particular phenomena might explain what we see on Bennu. And in the interest of time, I'll ask to go forward 2 slides, please. To slide 8. Okay, so here's another look at the Bennu data, which are plotted in black in differential format, compared with our model results. Now, because an impact outcome in this particular scaling relationship depends on both the impactor properties as well as the target boulder properties, we implemented a Monte Carlo approach, where for any given particular surface age, you expect a certain number of impactors, but the outcome of those impactors is going to be dependent upon the relative size and energy of the impactor and the boulder. So we repeated this experiment 100 times. And the purple data are the median of our 100 simulations. And I apologize, the plot is correct. The plot says 2 million years. Text is incorrect. It says 2.6. It should be 2. So it's the median outcome for 100 simulations of a 2 million year flux in the NEA population, using that Satsumi and Sugita 2018 scaling relationship.
2 minutes.
And the gray band, thank you. The gray band is the 99% range of the modeled outcomes. And you can see that our models match what we call the fishhook shape of these small diameters very well. And thus we conclude, in fact, impact armoring is indeed the explanation of the SFD that we see at small diameters. Next slide, please. Impact armoring introduces some very interesting variability in the formation of small craters. And one variability is that a single-sized impactor can actually generate craters of different sizes depending upon the target boulder. And this plot shows the impactor diameter on the horizontal axis and the crater diameter on the vertical axis for both gravity scaling, which is the green line, and for various strength scalings, the different black lines, as well as the Satsumi and Sugita scaling relationship for different target boulders. And you can see that depending upon the target boulder size, a given sized impactor will in fact make a different sized crater at the small diameters. The other point here is that the scaling relationship, because of its dependency on the boulder disruption energy, can actually act like a target strength. And this target strength variability can span up to 3 orders of magnitude or more. So you can have a wide variety of outcomes, even for a given impactor, depending upon what the target boulder is that the impactor strikes. Next slide, please. Okay, so there are some really fundamental implications and consequences for planetary defense. On a rubble pile asteroid, the same projectile can have many different outcomes depending upon the target boulder. The impact energy may be transmitted to the bulk object efficiently, or the impact energy may be dissipated largely by disrupting the boulder. And as Andy said earlier, in response to a question, you're absolutely going to transmit the momentum into the target, but what kind of enhancement you get by the ejecta is going to be very different depending upon the nature of the boulder. So an important consideration of the DART mission is understanding the boulder distribution at the point of the impact site. And looking into the future, any impact deflection mission should consider the outcome variability that's introduced by the size of the target boulder or boulders at the impact site. Thank you.
Thank you. Oh, perfect. Yep, we need to go ahead and move on. Thank you so much. The last talk before we go to our Q&A will be Dr. Michael Nolan, who's research professor at the University of Arizona. Observations of Bennu's increasing rotation rate, an implication for Bennu's evolution. Take it away.
All right, thank you. So as you can see by this list, of course, this is the work of a whole bunch of people cooperating to get these work done. Next slide, please. So I'm going to talk about basically the rotation state of Bennu and what we've understood about it over the years. Originally, we had ground-based visible light curves taken in 1999 and 2005. And of course, the ones in 2005 were taken shortly before Bennu was chosen as a spacecraft target, so they were pretty nominal observations. This is typical. You get a few days of light curve observations, you get a rotation period accurate to about 0.1%, which is really what you need for any kind of physical prediction, but it's not good enough to measure any long-term evolution because you can't maintain phase over multiple years. Bennu has a pretty low amplitude light curve with 3 peaks in it, which is consistent with its round shape. Next slide, please. So we were interested in we became interested in the detailed rotation state in order to help plan the mission. If you just look at 1 year, we had an uncertainty of about, Liza said, 0.1%. If you combined the observations we had at that time, you ended up with a comb of possible periods, but you couldn't choose between them. And so, next slide, please. So as has been common, we were unable, Bennu did not cooperate. We were unable to get telescopic observations from the ground in 2011. Just something always went wrong. So we did get 2 epochs of HST data about 3 months apart, and that did unambiguously determine the period. So the purple curve, it was determined to be the correct curve. Next slide, Pete, please. And if you plotted the data against the model light, we had a radar shape model at this point, so we could compute a model light curve. And on the left, you can see the model light curve compared to the data, and you can see that there's pretty clearly a phase shift. If you add a small YORP correction, you can correct that phase shift. And so this was what we essentially announced this as a detection of the YORP effect on Bennu, but of course it was always possible that there was just something else that might have had an impulsive change in the rotation period. Maybe there was an impact, maybe there was something else. It was difficult to really prove that this was YORP, but we could see that the rotation period was changing slightly. Next slide. As we approached Bennu, we figured it would be that would just solve it all together. But it turns out that, as is often the case, comparing spacecraft observations with ground-based observations is difficult because the observing conditions tend to be quite different. And in this case, we had a much lower phase angle from the spacecraft. And so the purple curve is the prediction of the ground-based shape model, and the blue curve and the points are the data we got upon approach to Bennu. And basically, because the scattering function is not well known, we were unable to, that gave us a lot of uncertainty in comparing those data, and that's going to turn out to be important later. And this is going to be true for any situation where spacecraft observations are going to be taken under different circumstances, and it's going to be difficult to compare them. Next slide, please. And you can see this again. On the left, we have the radar shape model and the radar compared to the 2005 light curve. And then on the right, we have the OSIRIS-REx shape model, which is far more accurate compared to those same data. And so it's uncertainties in the scattering, in the visible scattering of Bennu that are giving the rise to these differences. There's just places where it doesn't match. Next slide, please. All right, but but then we also, of course, were at Bennu for 2 years taking extremely high resolution data. So on the left, you can see a combination of the light curve data points. This is the rotation phase. So if you have YORP acceleration, you're going to have a parabolic rotation phase, a linear change in rotation period. On the left, you can see the parabolic rotation phase using the ground-based data as the course points, and then over on the right is all the proximity operations. If you look at the right-hand plot, you'll note the y-axis is, of course, much smaller. It's a couple tenths of a degree, which is tens of centimeters on the surface, but we can actually measure that. And you can clearly see over the 2 years of operations at Bennu that there's a parabolic rotation phase change. It would have taken it did take about 1 year to really be sure we were seeing it at Bennu. And anytime you're looking at something with a parabolic change, when you double the interval, well, it gets 4 times as good. So it's right now after 2 years, it's very clear that there's a rotational acceleration at Bennu. Next slide, please. So taking out that acceleration and just looking at the residuals, on the left, you can see the ground-based data points with their large uncertainties, and on the right is the spacecraft-based ones. There is a hint of possibly a change in the acceleration, but it's significantly less than it's not statistically significant. It's just sort of an appealing hint, which would be interesting, but there's nothing no way we can really confirm that now. And a lot of that had to do with that difficulty in comparing the photometric observations. So next slide, please. If we just look at the spacecraft, now that we've agree we understand it, and just blow up the plot to show the residuals and the proximity operations, there's this approximately sinusoidal residual in the phase, and with a period of 1 Bennu year. And so we said, gee, is the YORP really changing over the course of the mission? And so next slide, please. So it turns out that the rotational torque, as a function of where you are in the orbit, is proportional to a bunch of things, but there's you can see that there's a C0, some constant rotational acceleration, and then another component that is proportional to the sign of the true anomaly. That's what F is. So there should be an annual component to the acceleration, and that the change, that delta theta, is also proportional to the anomaly. And what's going to be interesting in the future is that these two constants, the continuous part and the sinusoidal part, depend differently on the shape and mass, and that's something we're going to be investigating. Next slide, please. So if you just plot the V-split cosine to those data points and the solar latitude, which has that same variation on orbit phase, you see that they line up perfectly. So essentially, we are seeing the annual component of the YORP acceleration on Bennu, which pretty well confirms that it is what we think it is. Next slide, please. Right, so the variation along the orbit finally proves that this really is the YORP effect, or to be my own devil's advocate, at least something that depends on the solar radiation. That we have this understanding of what, based on our model of what the torque should be, we can work more to see how these two different effects will depend differently on shape and mass. There are several things at least that go into the continuous part of the torque, and we're going to be examining those details in detail. So next slide, please. So what are the implications of this? So both Bennu and Ryugu have obliquities very near 180 degrees, but neither one is rotating near its breakup speed, nor is it stalled. So there's evidence that something like YORP is going on from lots of things, but it's clearly doesn't appear to be dominating the situation. Bennu's rotation is accelerating fast enough that it would break up in about 1 million years from now if it continued. On the other hand, Bennu has surface features that appear to be quite old, much older than 1 million years old, in predating its history near its space. And it also has features that could be driven by recent YORP-induced slope changes. So we don't see like huge landslides but we'd see something that looked like landslides. So just based on the fact that we see a lot of old terrain, it doesn't appear likely that it's going to accelerate to break up. And the conclusion is that YORP is affecting the surface, but it doesn't appear to be the dominant effect. Maybe it's self-limiting. As the YORP happens, it changes the surface, which changes the YORP. On the other hand, there are objects that are spinning near breakup. And so I think we still have a lot of understanding yet to go of what's going on here. That YORP clearly is driving objects to essentially their spin breakup, but not all of them. We're just going to have to keep studying this to understand that. I don't think the YORP itself don't think has any direct implications for any sort of planetary defense thing. I mean, the fact that Bennu is accelerating doesn't affect how we would treat it. It definitely, though, does affect the population of objects that we have to look at, and probably does have to do with, to some extent, the distribution, for example, of spin rotation poles. Thank you.
Thank you very much, Dr. Nolan. I'll turn the time over to my co-chair to moderate the Q&A.
Hi, this is Christian. Now, should we just read the questions from the Q&A first? I have a question here for Dr. Bierhaus. If impact armoring is responsible for reducing the number of craters with diameter less than 2 meters, what size impact does this correspond to? Or perhaps equivalently, what is the characteristic grain size for surface grains on Bennu? Bo?
Thank you. So the impactor size, again, well, the crater that you make is a function of the impactor size. So if we're losing craters less than a few meters in diameter, we're talking about impactors that are less than a centimeter in diameter. We're talking about, maybe 5 millimeters or something of that order. And then for the grain size on Bennu, one of the things that we can see in the images is we can see the boulders, and a lot of people did a lot of hard work to measure the boulder size frequency distribution. A recent paper came out on that. And we actually use that size frequency distribution in our modeling. And we were able to have the results line up very well, as I showed in my plot, where if you use the observed boulder size frequency distribution, you end up getting that fishhook shape in the right spot. If you had a different size frequency distribution, the horizontal location of that peak size would shift.
Okay, thanks. Now, I see an earlier question that I think might be addressed to Amy. It says, are you concerned with any planetary protection backwards contamination issues with your preliminary examination of the sample?
So once our samples return, we're going to follow standard planetary protection protocols. It will be collected from the Utah desert and brought to Johnson Space Center for curation. So there's already a planetary protection plan in place for dealing with the samples, following all the standard protocols. And of course, we were very careful about not forward contamination as well, making sure that the spacecraft was very clean and everything was documented. So I don't think there's any particular concerns. I don't know, Mike, if you want to add anything.
Okay, thanks. We have a recent question, which could be from the timing for Mike. Can it not be your effect, but the scattering law?
So perhaps the original detection could have been the scattering law, the one, but the current ones are definitely not. The current observing conditions are pretty repeatable.
Okay, do we have any other questions here? I don't see any more on the Q&A here. Anybody else have any questions?
One question that was in the chat from Mike Nolan, just in case anyone might not have seen it, was from Tom Statler. Can you link the observed acceleration with the thermal data and say anything about the normal versus tangential YORP?
And the answer is that's exactly what we plan to do. This is really a very recent discovery. It's only a month or two old. And the various different kinds of YORP should have different sort of average behavior versus variable behavior. And that's exactly what we're going to try to figure out. Because tangential YORP is something that's been sort of hypothesized as why YORP doesn't behave as the way it's kind of the way we've thought it did over the years, and it's also fairly recent, and so we're excited to be able to distinguish those.
Okay, do we have any other questions here from anybody? Any of the panelists have any questions? We still have plenty of time. Everybody answered all the questions.
I can ask a question. This one will be for everybody, but if you were thinking about designing a planetary defense mission for reconnaissance, for example, based on what you've learned for OSIRIS-REx, what would you say are some lessons learned that we should take forward for characterization missions for planetary defense purposes?
I think one thing is something we all know, but often fail to sort of state clearly, is that we know we will discover things we don't expect, and so it's a really good idea to have some space in your mission for things that are going to be observations, changes to the observation plan and observations you weren't expecting to do. One of the real advantages we had, almost just because of the dynamics for OSIRIS-REx, is we had a lot of time. And so we were able to say, we have to add a month of observations here in the middle that we weren't expecting to do, but to solve a problem that we discovered when we got there. And the whole point of exploration is to find things you didn't expect, and so you'd better be prepared to actually have that happen. To the extent you can.
Anybody else want to reply to that as well?
Sure. I mean, I think following on what Mike said, also the breadth of the instruments on OSIRIS-REx covering such a broad wavelength range, having, LiDAR plus cameras plus spectrometers really of course, gave us a better science return, but we learned a lot more about the surface by having that big, broad wavelength range. So, you know, don't undersell it as just being science. I think you learn a lot about the surface by having that big, broad coverage.
And I'll give a response that is talking about Bennu, but also a little bit about Ryugu. The two bodies in some ways look very similar. I mean, they have a similar shape, they have a similar albedo. We expect compositionally there may be some similarities. But now after Hayabusa 2 and after OSIRIS-REx, we now know that these two bodies also have potentially some very important differences in terms of composition. And so I think this is just to underscore what both Mike and Amy said, which is that even these two bodies that telescopically and as points of light and you know, might appear similar, could actually end up being fairly different. So maybe one lesson is that at least based on what we know now, every object we go to is different, and there are a lot of asteroids. So I don't know that we want to plan a million different reconnaissance missions, but we should not necessarily assume that one object we visited is going to be analogous to some object we haven't visited. Just because there seem to be some very peculiar and unique evolutionary pathways that an individual body could take. So I guess the lesson is don't assume that once you've seen one asteroid, you've seen them all, because they all appear to have different stories.
I see a couple of other questions on the chat, on the Q&A, but before so, actually what Bo just said brings up a question that I would have had, and I don't know who wants to answer that, if any. Now, the density of Bennu seems to be indicating that maybe it is not a solid body. And if we're looking at the target of the HERA mission, I think that's quite a different beast of an asteroid. Now, what would happen in the case you'd have like trying a deflection mission on Bennu? Would that result in just like a sandbank breaking apart, or actually how do you transfer momentum in such a case? Anybody have any idea on that?
Well, this is Bo. We do see impact craters on Bennu, and so we know that energy and momentum has been transferred into the surface by things hitting it. As Ron's talk showed, that if you get down to very small sizes, you're no longer making craters in the surface, you're maybe making craters in the boulders on the surface. And so depending upon the size of the deflector you bring to Bennu, and depending upon what size boulder you actually end up hitting, you could primarily disrupt a collection of boulders on the surface, or you could actually end up making a more traditional, well, traditional maybe isn't the right word, but you could make a crater kind of like those that we see on Bennu. They do span, you know, up to 150 meters or even 200 meters in diameter on Bennu. And so it would be able to survive any sort of kinetic impactor we could throw at it. It would just be a matter of calculating what the crater size would be.
Okay, thanks. Now, I have a question on the Q&A, which has been answered sort of, but maybe somebody has a comprehensive, non-technical reply. What exactly is YORP? Nice abbreviation, nice acronym, right?
So actually, the answer that Tom Statler tried to give is about as good as you can do simply. So
it's what the acronym stands for.
It's YORP is a response to sunlight hitting the surface and essentially being radiated in an asymmetric way, which actually applies a torque to the body over time. I mean, you wouldn't think that sunlight would would twist things, but if you have the right kind of body and the right, there is a small rotational twist to the effect of the sunlight on the body, and it's very small, and it in principle can go either direction. And it's been proposed about 30 years ago, and it is clearly there.
Wow. Radzievsky and Paddock. So those were 4 guys who worked on this. That's what the acronym comes from. Anyway, next question. Following up on this, if you don't go for a sample return or lander mission for a PD characterization mission, how close would you need to get to the asteroid to get good results like OSIRIS-REx or Hayabusa without the sampling? And would it help to have a small and rugged scouting lander like Mascot or Minerva?
I think for the remote sensing part, it depends a bit on your instrumentation, of course. Some of it is capable from far out. For the OSIRIS mission, we had our mapping phases were at 5 kilometers, 3 kilometers from the surface, but our recon passes went as low as 250 meters. But that's really dependent on, again, the spatial resolution of your instruments and how well they can handle the environment close to the asteroid. Bennu being near Earth is pretty warm, so things do get heated up when you got close to the surface. In terms of gravity or something like that, I can't really answer. I don't know, maybe Bo might have a better answer on that one.
Just briefly say that one of the best ways to understand the surface properties of something is to physically interact with it. And so if you are able to carry a small lander like Minerva, that would certainly help in understanding the response. We are gaining a somewhat better understanding of impact cratering in rubble piles, and that provides some constraint if you're limited to remote sensing. And so I think there's some help there, but certainly if you have a small lander and you can actually contact the surface, that's one of the best ways to constrain the surface properties.
Okay. Which answers an additional question. So do we have any more questions from anybody? We would have another 5 minutes. Just in case.
Hi, yeah, this is Bill Ayler. I'm curious, a very interesting session. I'm wondering, given that every asteroid you visit is different, we wouldn't know what kind of an asteroid might be a threat to us when it's detected. And if we had to do a fast flyby of that thing, what do you, based on your work, do you have recommendations on what kind of measurements you could actually make in a fast flyby that would inform planetary defense?
To some extent, we've been looking at this because we are thinking about doing flybys in the future, and our instrument seat was specifically designed to get up close, right? So our cameras are relatively low magnification, for example, but several of the other in-progress missions, things like the Juno mission and a lot of the other characterization missions have had much higher sort of longer focal length cameras so that they can get longer observations from farther away and over longer times. Mm-hmm. And there's some things like you're not going to get you're not going to get a complete rotation of the object like that, right? You're going to get a snapshot, or and so you're not going to get nearly as complete of a characterization. We went for, as Amy said, complete spectral coverage, but that at the expense of resolution, you probably are going to make the opposite kinds of choices when you have short encounters like that. So basically, it's just if you're going fast, you're going to have a short encounter. So you've got to be prepared to take data as fast as you can, and then send it back when you're ready. Right? Our cameras could only take the data sort of once a second. You'd go faster than that if you could.
Okay, thank you.
Okay. More?
I have a question for Ron. Ron, in the studies that you were doing of boulders and looking at that transition between strength and gravity, to what extent do you think that depends on composition? I mean, clearly, this is a Bennu is Bennu, right? It's a dark object, and there are lots of dark objects. But how might you think about extending that to other types of asteroids?
That's a good question. I guess if we wanted to extend the results of cratering or any strength measurements of boulders on the surface of these things, whether it's from the craters or the mascot result or thermal inertia, you have to consider what is feeding the population of NEOs of that size, say 200 meters or less. Is it directly from main belt reservoirs? And thinking about where exactly from the main belt would you source this size or class asteroids, and if it's in a collisional equilibrium or not. So for example, for S types, it's hard to say, but based on observations of Itokawa, you also had largish boulders up to 40 meters or larger. We didn't see much craters on them, so that could be a reflection of their strength.
Okay, thank you. I think we're probably coming to an end of the first day. I don't see any more questions here. If anybody has a real urgent question, speak up now. Okay, I don't see anything, I don't hear anything. So let me thank, first of all, the speakers in our OSIRIS-REx session for their great contributions. And let me thank my co-chair, Tarek Daly, for doing the brunt of all the work, organizing this session. And let me thank all the organizers, and especially Jenny for taking care of all the slides here. And I think this concludes today, and see you tomorrow.